Okay, I think it's time to get started. First of all, welcome to Rennes and welcome to VMCAI with my two co-chairs. We're very happy to see you here. We find that we've have a very interesting scientific program to propose you. So whether you are just staying for VMCAI or whether you also want to join our satellite event the rest of the week, I'm sure you'll have a nice scientific experience here. Before introducing our invited speaker, there was just one little announcement. What was now? I've forgotten it. Sorry? Right, okay, yeah. So we've added a small PC Chairs report this afternoon after the last session, just a quarter of an hour. So if you're interested in that, please stay on. And there will also be the awards ceremony. Oh yes, we have two distinguished papers that we'll reveal at that moment as well. So we'll say a bit more about how the PC worked, but I think we'll just get started with our invited, which is David Pichardie from Meta. David is known worldwide for his work on abstract interpretation, on work with proof assistance, in particular ROC. And in particular, the combination of those two, he was one of the first to actually do what we called certified abstract interpretation here. So he has a PhD and a habilitation here from the University of Rennes, where he was first working as an INRIA researcher and then as a professor at ENS Rennes, and now as with Meta. So over to you, David, and for about 45 minutes, 50 minutes of talk.
Okay, thank you very much. Thank you for the program committee for inviting me. It's a great honor. It's also a great honor to present the state of this great project, INFER, which has been here for more than 15 years now. I play at home today because I work from Rennes, full remote. And yeah, I will try to present what is INFER, what are the current state, and I hope I will give you a better understanding of this project. So the first best way to start is to give a demo, or mostly a demo because it will just be on slides. So imagine you have two Java files with two functions in each file, and okay, you want to check if there is something wrong. You ask INFER, and INFER will tell you there is something weird here. And the kind of reasoning that INFER is doing is really interprocedural. So behind the curtain, what INFER is doing is understanding that the first call to foo is going to this function. INFER is understanding that in this function, you will call another function, which will return null and set your A field to null, so that when you go back and call this function, here you will dereference a null pointer. So this is really a reasoning about interprocedural steps, okay? And INFER is really trying to follow all your call graph edges and give you some very actionable signals. Today, what I would like to explain and present is what in my opinion, make INFER a success in industry, and what make it a singular point in terms of design choices. So I will try to focus on very specific features, mainly three of them. The first one is that we have a common IR to all the front end we support. So there is a big work around intermediate representations in this project. The second point is this motto that we can start from anywhere. I will try to explain a bit what it means. It is related to the specific interprocedural technique we use here. And at last, I will explain a bit why and how we try to favor false negatives over false positive, because we really care about the quality of the signals we send to developers. So, but first, because now it's an old project, I want to spend a few minutes explaining a bit the history of this project, because many of you are too young maybe to know that, but you need to know about this story. And you can hear me, but at some point you will also need to read this article by Peter Owen, where all this story is well explained with far more details. It is the CACM paper. So, in a sense, it all started with Tony Orr, because Tony Orr presented this idea of Orr logic to prove correctness of programs. When you go back to this time, it was quite a theoretical contribution about giving semantics to programs. And still, there is a clear link with what I will present today. So it's a first, I think, amazing point. A major step a few years after was about inventing a logic which reasons well on pointers by Peter Owen, Reynolds and others. So separation logic was also a great milestone for the infer story. At that time, even if programs looked a bit more realistic with pointers, it was still quite a theoretical contribution, because it was hardly believable that it will scale, because you still have to annotate all your program with pre, post, loop invariants. So scaling to millions of lines of codes was not clear. And this is what Peter and his colleagues focused on a few years later. So they invented this notion of B-abduction, which is really a way to infer all these annotations that program logics require. And the first experiments proposed by this paper were really encouraging. They were analyzing a Linux kernel, for example, at this time. And I think at this point it was clear that there was a clear potential for scalability. They were also very motivated by having impact in industry and real life. And they founded, three of them founded a startup, Monoidix, 2009. And 4 years later, yes, the startup was acquired by Facebook. So extremely quick process. They were invited to give a demo at California HQ. They analyzed Facebook code there. And 1 week later, the deal was done. So very impressive movement with announcement in newspaper. And yeah, in 2026, Infer is still there. The company is named Meta now. By the way, it's an open source project, so it's not only for Meta. And yeah, every day at Meta, people submit what we call diff, which is kind of pull request. It goes to an environment, a CI, named Fabricator, also a nice open source project. It goes to the continuous integration, yes. You need a human reviewer to accept your pull request, otherwise it will not be landed. But there is also another tool in the loop, Infer. We will check your code. And it is happening every time, every day. It's happening now. Okay. And yeah, it's really an example of scaling to industry. If you look at the numbers, we have thousands of developers in this company. They maintain, develop more than 10 of millions lines of code, far more. And we have hundreds of code changes per day. So we need to go fast, we need to scale, and we don't want to waste this developer time. Okay, that's why I will mention false positive and false negative in the last part of this talk. So, for me, the first learning outcome of this nice story is first, principal research can be impactful. It can take a bit of time. Okay, you start from tenure. But at the end, I think Infer is a real example of impactful research that is born from this community, programming languages, static analysis, semantics. So maybe you can reuse some of these slides in your course or examples when you want to explain to people why you are doing your research. Okay, now the first feature I would like to explain, is this notion of common IR. So if you are familiar with LLVM, this is something a bit similar. This picture looks a bit like what LLVM is, but Infer tried to do the same for static analysis. So we have one common IR at this center here, and we translate many source languages to this IR, and all the analyses share a common analysis platform. You will have more details in the rest of the talk. I will also mention that all these front ends do not have the same maturity. Some projects are still ongoing. But there is really this idea that we don't develop a new platform for each time we want to analyze a new language. And in a company like Meta, you really need this flexibility because you will have to adapt to new languages. Okay, the new languages will come, and hopefully you will be able to adapt your static analysis platform. Just to mention, in this talk, I will give you a lot of details about the core elements of this platform. I will not mention so many examples of analysis because you will see that from these core elements, you can develop a lot of different analyses. Okay, let's zoom a bit in. So we have all these front ends, and they will all be translated to a same intermediate representation, named SIL for Smallfoot Intermediate Language. So Smallfoot was the first name of the tool before Infer. And then we have the backend analysis, where we use a lot of well-known academic techniques, abstract interpretation, incorrectness logic, SMT solvers. And all these analyses can reuse some of these elements, maybe not all elements, but some of them, to do their own work. And sometimes one new analysis is really a small configuration of this element. You don't have a lot of work to do for your new analysis. So I want to start by giving more details about this IR. So in 2022, we managed to renovate a bit this IR because there was a need, because it was not so easy to emit this IR. So every time we wanted to add a new front end, the workload was a bit high. Indeed, this IR was not meant to be written by humans. It was really meant to be used by analysis tool. And we wanted something cleaner, easier to manage, to emit, and also easier to understand. The project was already old, 10 years. So this new IR here, which is named textual, because you can really see the text representation if you want. You can adapt it just a few characters and re-emit them to the analysis if you want, a bit like the LLVM bitcode. So yeah, this idea is that we want to facilitate addition of new front ends, and we want to better understand the intermediate representation. So indeed, after 2023, all the new front-end were directly based on this new representation. So, so the last two are work in progress, Rust and Swift, which go through LLVM. There will be a nice talk today about this new front-end. And some recent front-end about Python and Hack, which is a typed version of PHP. Were directly using this new IR. So this is an example of program in this IR. Very factorial, of course. You need to give an example with factorial. So a module is composed of function, type declarations, and prototype declarations. This is just an example of function. A function is a control flow graph with blocks. Each block has a name. A block is a sequence of instructions, and it ends with a terminator instruction, like in LLVM. A terminator can be a jump to several successors. And inside the block, you can use the prune instruction to constrain the current instruction. And the semantics is that you are stuck if the Boolean test is false. Okay, so it's very standard, I would say. But it is really a language. It has a syntax. You have some tools that help you write some well-formed programs. There is a type system. We will catch many errors. And there is also an inference type mechanism so that you don't have to write all the types yourself. And some high-level construct, like you can declare a closure, if you want, inside an expression, and it will be transformed with the right encoding later. So yeah, you can emit a lot of code easily with this new language. And we have algorithms to transform, compile all that into the old internal representation of infer. Okay. And yeah, in terms of impact, it was quite successful in the sense that we were able to mostly develop a new front end each year. So we were really happy with this new IR. And yeah, it's really a core language. So all the languages here. This is the OCaml abstract syntax of this language. So it's, in my opinion, really amazing that you can turn all these complex, realistic source languages into one common IR and just try to reason on it. Of course, it is not that easy, but if you think about it, it's a great lesson. This is my second lesson for today. You need to remember your compiler courses. It's amazing what you can do with a good compiler technique. And LLVM is a super cool example of that. Of course, I don't want to give you only the good story. Of course, it is not that easy to have one common IR. So it's a matter of trade-off, of course. Of course, all the backend analyses are not completely independent of the source languages. You sometimes have to check what is your source language. So in some places in the analysis implementation, you will see some tests like, if I am analyzing Java, then. Okay, there is no free lunch, but still many parts are shared. Of course, second point, is not that easy to compile to a single, simple, intermediate representation all the modern languages ahead of time. Think about Python, for example. So if you look at the Python front end currently in Infer, you will see that even so, we have only 4 instructions in this core language. Okay, store, load, the prune I have presented before, and a let, which is a way to do some calls. And in Python, we just emit let because everything is thrown to a built-in call. And later, each analysis will have to understand how to interpret this built-in. So this is still a common IR, but in fact, we do not share so much at compile time. During analysis, we have a way, I will not present that today, we need another talk. We have a way to reuse a lot of the common architecture when we write the transferred function for each built-in. So it's still there is still a lot of reusable work. But yes, there is no magic weapon. Compiling ahead of time modern languages is not that simple. Other points, there is a famous motto in static analysis. Analysis source language enable more subtle abstraction of high-level features. So if you think, for example, about Astray, was a very successful industrial scale static analyzer. It works at very high level, very close to C. So Infer took a bit the opposite direction. I think we partially mitigate this problem thanks to the highly symbolic abstraction we use and the highly precise heap abstraction we use. And you can also look at Mathieu Lemaire's work, where he explained well what symbolic execution abstraction, how it helps you to recover part of this problem. But yeah, we are a bit at the extreme of the line around this choice. And so yeah, at the end, I think it was really a winning trade-off. And it's not only about science, it's also about engineering cost. So if you have a new engineer coming to your team, maybe this person is not a PL expert, he will be able to reuse a lot of elements. He will see a very simple language. So he doesn't have to be an expert in Swift, Java, or C++ immediately. So I think the learning curve is also very interesting in terms of engineering. And as a PL enthusiast, I must say it's so cool to be able to deal with all these languages in the same platform. So myself, it's really a pleasure. Okay, so it was for explaining a bit the state of this intermediate representation. Now let's talk a bit about static analysis. So in fact, after emitting this IR, we go through an AI framework where you can plug many abstract domains. Today, I will present a bit the AI framework, and I will also zoom on this specific abstract domain named POPL', which contain incorrectness logic and SMT solvers. But first, a bit of AI framework. So some parts are extremely standard. The intra-procedural part is really the textbook abstract interpretation approach. You have this notion of lattices, this notion of transfer functions, join, widening. We are working on the control flow graph, remember, so we need a good iteration strategy to find the fixed point. So we use the well-known technique named Bourdoncle strategy using graph algorithms. So yourself, if you just want to write a new intra-procedural analysis inside Infer, you just need to open a simple textbook and implement very basic operators. So it's very simple. The interprocedural part is more tricky. I think static analysis experts in the room will acknowledge that this is the hard part. Scalable interprocedural analysis is really hard. I will not claim there is only one solution to solve this problem. I think Infer is solving part of this problem and it is solving it very well, taking into account its own industrial constraints. So what we use is this summary-based compositional analysis technique that I will present. We use parallel computation to traverse bottom-up the call graph, and we perform an on-demand exploration so that we don't need to build the call graph first. So let me give a bit more details. I'm not sure everyone is familiar with the interprocedural landscape, so let's switch to a crash course about that. Imagine this is a control flow graph. Each box is a function, and a function is calling other, and so on. If you start, okay, you know how to do an intraprocedural analysis, and in your control flow graph, you have goto, you have jumps. So maybe you can already do that interprocedurally. Why not? Indeed, you can. This is what we will call naive context insensitive analysis. And what will happen is that when you go here, you will join all the colors, states, and when you will jump back, you will use the context that is at the end of this function. So you will merge a lot of context. You will also invent paths that do not exist, indeed. So it's extremely simple design. Mostly you can just reuse your intraprocedural framework if you want, but do not hope for a lot of precision doing that, because you will, for example, you will invent a path like I jump here and I return here. So this invisible path, which is considered by this analysis, it will lead to a lot of loss of precision. So very scalable, can be very quick, but don't expect a lot of precision here. If you want better precision, you need to be context sensitive. So now, if we name a bit the calling context, we will analyze this box 2 times, in a sense. We will analyze it with a context 1, and this context will, and this color will benefit from this specific analysis. And we will reanalyze, in a sense, this function another time and benefit from the specific context here. But we have to continue like that. So here you have a multiplications of contexts. So you have more and more context to consider. So at the end, you gain a lot of precisions, but scalability is far harder. And if you look at the big picture, to do such an analysis, you really need to take into account cyclic dependencies, because the callee depend on the color context to know how with which information to start its specialized analysis. And the color, of course, depends on the callee analysis result. So these mutual dependencies has very bad consequences also in terms of scheduling your analysis. And most of these techniques are used in a setting where you need to know where are the entry points of your program. So if it is a big web page for a social network, for example, I don't know, you have many entry points, very complex, and you need to start your analysis from there. Okay, you cannot start from anywhere. You can still use this notion of on-demand. There is a literature about that. You can try to be a bit lazy, of course. But this is not exactly the same setting that the next technique, which is compositional interprocedural analysis. So here, the main tool is this notion of summary. So for me, a summary, it's a big formula that represents the behavior of an individual function. So it's like a book filled with formula. And this formula is expressing the behavior of this function, but without any assumption about the calling context. So it means you can start this analysis even if you don't know what are your colors, okay? And then, once you have these books, you can build this summary here, and you can build this summary, and so on. So in this approach, you really want to be able to start from anywhere. You have removed one important dependency because now the callee does not depend on the caller. So it will also help with the scheduling. You can use dynamic programming, in a sense, to perform the global analysis. In fact, we don't do that because we still want to be a bit on demand and only analyze the functions that looks necessary for the current fragment of code we analyze. And in theory, you should only have one summary per function. And this summary will be used by all call sites. So this is a compositional approach. A demo, you start from this function here, hey, and you call B. So you don't know who is calling a.f, you don't care. You want to build a summary for f. You see a call to j, so you jump to j. You see a call to h, and here h, imagine you don't have calls anymore. So you can build your summary. You store it somewhere. Maybe it will be reused later by others. You go back. Same for function e. You build a summary. And when you reach this point here, you can reuse this call. You apply the formula in this context. And if your logic is expressive enough, you have a very expressive formula in your calling context. And you can go back. So this is really what we call on-demand. This is not the full bottom-up dynamic programming approach. We wait for having a proof of need to perform a summary computation. But we only build one summary per function at maximum. So it's linear in the number of functions. Okay, but in this previous example, all the calls look so simple. Static calls, it's very simple. The name of the callee, it's written there. And you must know, if you program in modern languages, that is not that simple in real life. So think about virtual calls. So this is a virtual call to method m, but who is m? To understand who is m by the object-oriented approach, you need to know what is the object O, what is, how was it constructed, what is its runtime type. So this is a very implicit call. This is not a static call. You can have closures. So this is a closures with a very nice syntax of Objective-C. So for me, it's always a pleasure to write this syntax. You apply. This is you have one parameter, and this parameter is a function of type integer to void, and you just apply it to 0. But you don't know what is this f. You need a value analysis to understand who is really called here. Another well-known example, function pointers. You don't know what function will be called exactly here. This is a pointer to a function. And in a recent work around PHP hack, we also have this beautiful notion of let static binding. So there is a lot of static calls in PHP, but in fact they are not so static in a sense. This is me explaining this notion. So yeah, again, a very implicit call, and you have to deal with that. And what I found very nice with the current approach we had in Infer is that first, we translate all this notion to a single notion of implicit call, which is mainly virtual call. We choose virtual call to represent all these notions. So using compiler techniques, we translate all this notion into one, and we try to have a very robust technique for virtual calls. Let me explain. So what happened with virtual calls is you have all these callers, and they call function foo, where there is a very implicit call. You don't know which M is called here. So what you could do, a naive approach, would be, okay, let's imagine I know all my code base, I know all my class hierarchy. So if I have a good type system, which sometimes I don't have with the modern languages, but imagine Java, for example, I can look at the static type of O, and I will find another approximation of all the potential callees. Then I can make a big union of all the possible behavior. But good luck with the size of the summary here. The summary will probably be extremely big. And in practice, at runtime, think about Python, you probably will use very few of these callers. So it's really a waste of resources because you are joining a lot of potential behaviors, while in practice you only use very few of them. So we don't want to do that. And to address this problem, we change a bit the way we use summary in Infer. We introduce this notion of summary specialization. So there will be another talk today about that in the same workshop, TPSA workshop. And yes, so summary specialization, this idea is that, okay, we will allow a function to be analyzed several times, but for various specialization keys or calling context, in a sense. So it's really a mix between the two context-sensitive interprocedural techniques I have presented before. If you think about virtual calls, the information you need for specialization is really related to runtime types, okay? And we will ask the caller to give us a specialization key. So let's just give you a demo again. We start with function f, which is really nice because it only has static calls. Then we jump to b. We want to build a summary for b.j. And okay, this is a static call, fine. But when we go here, we see a virtual call. And to resolve this virtual call, we need to know what is the dynamic type of x. And we don't know. X is a parameter. So we stop, in fact, this summary construction. And we go back to the initial caller and explain that it will require some extra information. And if the caller has this information, for example, imagine here we know that y is of type C, we can send this information, and now the call here will be resolved. So it means we will build and store a specialized summary which contains an assumption about the parameters. If you are lucky, you will be able to reuse the summary. If you are not lucky, the next time you call G, you will use it in another context and you will need another summary. But you will do this process on demand. So you will only analyze a function with a specialized summary if there is a proof that you need this summary for your analysis. So it's even more on demand than before. Okay, so we have introduced this approach in 2023. As I will mention, these days we use a lot incorrectness logic, and this approach is far easier to understand and implement in incorrectness logic because at some point we can give up, in a sense. So if we run out of resource for building new summary again and again, we can just stop and cut the exploration. This is what incorrectness logic allows to do. So in practice, we have to bound the number of specialized summaries. We analyze more codes than before, so there is a time overhead, but there is also a clear expressiveness win with respect to all these implicit calls I have mentioned before: closures, virtual calls, let static binding, and so on. And what is nice is that if you know a bit about separation logic, you know that there is also some difficulties with aliases context, because during the construction of a specific summary, you will have to assume that some parameters are not aliased. In fact, it's an assumption, and maybe at the caller site, you will detect that this assumption is false. It's not a problem. You will reanalyze the same function with the alias specialization key, explaining that this time you want to assume that these specific cells are aliased. So it's nice that with the same setting, we are able to express very different notions and limitations. So third learning outcome, be compositional, in the sense that it's really interesting to have this compositional interprocedural approach. Interprocedural. You can start from anywhere. And it has this advantage that I call air pockets, because sometimes when you develop an industrial scale tool like that, maybe you will not have access to all the code base, for example. So some callee, you will not know them. You will have to skip something. So being able to skip in a compositional way a call is really interesting and I think important for the design. Maybe you will run out of exploration budget also, so you have to stop and you have to skip this call. Or maybe you have to deliver a new front end, a new analysis, but you are not completely done with all the features of your language, and you can just model some call very badly. But there is no free lunch again. I don't want to hide details. It's not so easy to have a good notion of summary. You need a good and expressive abstract domain to be able to express a formula about post and precondition. Because remember, you do not assume anything about the calling context. So it means you really need a relational abstraction about the pre and the post states. And in infer, because most of the techniques are based on separation logic, we will not only need to reason on these pre-post, we will need to infer them. Not only the post, but also the precondition. And this is really what is explained in the B-adduction paper I have cited before. And very recently, yes, we introduced this summary specialization technique to inject a pinch of call site information. And if you think about the compiler world, it's a bit of partial monomorphization that we do, because all the examples I have shown before were very polymorphic functions. Okay, so this is the AI framework, intra and interprocedural. Let's jump to the pulse domain. So yeah, I will try to do that in 5 minutes. So this is a very important domain for us. It has been developed recently by Jules Villard. So the idea is really to replace the whole B-abduction engine that was used in infer. We want to be very strong and very precise with pass sensitivity, because you can have a lot of false positive if you are not very precise with pass sensitivity. Coming from separation logic, we are extremely we want to be extremely good with memory reasoning, and we really want to favor false negative over false positive. I will explain that later, but this is really a new re-implementation of the bee abduction approach, but with this bug finding approach. The goal is to send signals which have a highly chance to be true bugs. So, crash course on Pulse. First, you need to understand a bit what is a symbolic state. So, in a symbolic state, imagine you have something like that at each program point. You will have a notion of symbolic value. So, this value is a set of symbols, fresh variables. You will attach such value to program variable, the names that were already here in the source program. And they represent the address of this program variable in the stack. You may also have some logical variables that have been introduced by the compiler, but you will not see them in my examples. And then there is this classical notion of points to in separation logic, explaining that this address points to a cell containing this value. Okay. And we can attach a lot of attributes to all these symbols depending on the specific analysis we want to do. This is the part that is really configurable and that we adapt every time we need a new analysis. And imagine you just have this C statement to analyze. So you assign the field. You will need this precondition and you will need this postcondition. Yes. So here we are explaining that we have named Vx the address of program variable x. When we dereference Vx, we find another symbolic variable VL. And VL, if you consider the offset next attached to this address, you point to Vn. And if you dereference Vn, you go to V0, and V0 is invalid. So we have many points to predicate used in this very simple example. Yeah, I don't know why it is animating. But this is just the base domain. And in fact, what we will infer and propagate at each program point is a triple of one precondition, one postcondition, and one pass condition. Pre and post belongs to this notion of base domain, but we really want to infer the precondition of the current function. So we will when we perform our intra-procedural abstract interpretation, we manipulate a triple here. And the pass condition, we are accumulating all the assumptions, all the prune statements that you have seen before, the assume, in order to have a formula constraining the current pass. So this is a full example of a function foo, where L is a pointer to a list, and we do the same assignment as before. When we will start the abstract interpretation, we will start with an almost empty state. Here we are just declaring that, oh, okay, it should be x, sorry, that x is a valid parameter. And after one step, we have inferred that, in fact, we need a bit more assumption about x. And we have also inferred that after this assignment, the content of this field is not a valid address. Okay? And every time there is a call, every time there is a prune, we'll try to check if some infeasible path has been detected. Okay? For that, we use the well-known notion of SMT solver. We have our own SMT solver inside Infer. We choose a very decidable fragment of theories. We have a conjunct of ground terms. We use a Shostak combination of basically the two theories, congruence closure and linear rational arithmetics. Of course, a bit of integer reasoning or nonlinear arithmetic is always good to have, but we want to keep a very cheap approach. So basically, we use some interval arithmetics to do that. And this is our own solver. It is incremental, meaning that every time you do a step, you just do a small modification of the current state. Everything is programmed in a functional way. So we have a lot of sharing, and this sharing in memory is really important for scalability. Especially because, in fact, what I have just shown is just one state, but in fact, we have a disjunct of state that we manipulate. So at the end, we are really doing a partial exploration of all the paths inside your function. Of course, we need a limit. Incorrectness logic explain what this limit means. And sometimes we just unroll some loops if we cannot find the invariant after a few iterations. Yeah, and what is nice is it is not just symbolic execution, because we have this very specific interprocedural technique to compose summaries. Okay, and to conclude soon, the outcome here for me is that signal quality really matters. We cannot afford to send too many false positives to developers. Their time is very precious. And we are not in an industrial setting where we will have 0 alarms soon. Okay, so it's a trade-off. In our setting, we want to make sure that at least 50% of our signals are taken into account by developers. If a specific analysis is below that, we will not use it in production. And with all this approach, here you have example of 3 recent analyses we have performed using Pulse and the recent front-end for Hack and PHP. And you see that the fixed rate are around 50, 80 and 77 fixed rate rate. Yes, so it's quite good for our standard. So to conclude, it's quite amazing that after 15 years, Infer is still delivering this impact at scale in industry. I promised to explain 3 features, but in fact there was 4, because I think the first one is foundational programming language research matters. Remember that. This compiler approach also is really interesting in my opinion. Compositional interprocedural analysis was really a winning approach for this specific setting. And the recent shift to incorrectness logic was also very important, because the false positive problem is really something specific companies cannot really afford, in a sense. So altogether, this is the end of my talk. And yeah, you will have other information today about the ongoing front-end for Swift. Yesterday, there was a talk by academic collaborator, Andrea Costas, explaining there is an ongoing project to add a Rust front-end. And we have some ongoing project or, of course, brainstorm about how to ride the AI wave. I will not detail them today. I just want to finish with the list of all the major contributors, mostly 30 major contributors. And these days we are only 5 working on the tool, but there have been a lot of great contributors. Thank you.
Thank you, David. We have time for some questions. There's a microphone here coming around. Katrina?
Thank you. I was wondering, so you have this intermediate representation where all these languages are compiled to, but how do you then report the errors back to the user? What goes into that?
Yeah. So each signal will have its own notion of report. Of course, during the compilation, we take care of program locations. That are really generally attached to names. There is a risk that sometimes some messages could not be attached to the right names, of course. But for me, location is not the worst. It's most that sometimes your front end will introduce new names. I did not mention that, but we rely a lot on other representation like bytecode representations. For example, we rely on the Python bytecode, we rely on the Java bytecode. These days we rely on the LLVM bitcode. So the risk here is you will mention names that only make sense in this lowest level representation. But if your toolchain is well engineering, there should be a way to understand if this name has been synthesized by the first compiler. So you can filter which name is really a source name or an intermediate name. And also in some situations, we try to recover a bit of this information. For example, we have a way to decompile. It's a best effort approach. To decompile a bit some names to give the name that has more meaning for the developer. So it's not perfect for sure, but yeah, I mean, in some situations there is a signals. It's not super easy for the user to read it, but maybe it will be enough because it's already a bug and the user will understand where it is.
Okay, thank you.
Okay. Another question over there.
Hi, thanks for talk. So you tell us your analysis is mostly used on diff. Could you tell us a bit more? Maybe I imagine there are some caching systems or the kind of information you keep, how you disable it, enable it, this kind of thing.
Yes, so we also try, so in a sense, for me, there are three and now four scenarios now where we want to use infer. First, at IDE time, will be nice to use infer. It's also something we already do, but we have to limit a lot the exploration depth. So it means we will not give to the analysis a lot of dependencies. So they will have to skip a lot of calls with this modular approach. But we already do that because, of course, people want to have instantaneous signals. Not that easy with an interprocedural analysis, honestly. Then we have this diff time approach, pull request, and we have what we call a conscan approach, where regularly we run infer on all the code base. In the past, there was a kind of incremental approach where we was trying to reuse the previous analysis result on a previous version of the code. But currently, we don't use that anymore. It's a great idea, but not so easy to maintain and adapt to every new languages. Would be great to reactivate that work. I think it's very valuable. And we just use a huge amount of resource we have to run massive parallel computation, few hours. But there is also a risk that you will report bug that was already there in the past. So we also use a heuristic to filter bugs that were already shown before. It's something where we need also to be good at. And the fourth notion now is AI, because we want AI tool to be able to run infer themselves. So for me, it's also a new surface. We want to make sure that this tool will know how to run infer. They will know how to read infer messages, and probably we will need to tell them something a bit new because they are capable of reading far more details than human. So we are also trying to adapt to that currently.
Thanks for the talk. I was wondering, how do you deal with exception?
Yeah, so in the intermediate representation I've shown, exceptions are still in the language. So there is a notion of handlers. The notion of handler for exception is quite well known, for example, in Java bytecode. There is a clear semantics for that. We use exactly the same. Then you have to decide if your analysis want to take that into account or not, because there is a risk also again of false positive. So it depends a bit. But for example, we have some resource analysis where we try to find bugs where resources were not properly closed, like opening a file. And for this specific approach, you really want to care about exceptions. So here we take them into account nicely. In Java, for example, we do that. Yeah.
Thank you.
Good. Thank you. In the interest of time, I think we have to move on. But let's thank David once more for a very interesting talk. And our next talk is actually a tool paper about MOPSA. Raphael?
Or okay. Okay. Thank you, Thomas, for the introduction. Good morning, everyone. So before I talk to you about TryMopsa, I'm going to explain to you what MOPSA is. So MOPSA is a modular open platform for static analysis that was started around 10 years ago by an ERC grant awarded to Antoine Minet. And I'm going to explain a few of the key design decisions about MOPSA. So one is we really try to allow users to customize their analysis through the composition of abstract domains that they use. A second is that we try to ease for developers how they can write highly expressive relational static analysis that are able to infer, for example, linear constraints between program variables or ghost variables. And we also think that it can be used as an experimentation platform. We support analysis of, let's say, large subsets of C and Python. And there are also ongoing works on other front ends. So, for example, you can attend Mila's talk this afternoon to learn more about compositional OCaml analysis that she's working on. And I think it's somewhat good in the sense that it's academically competitive compared to other state-of-the-art tools that have been developed by really large groups for plenty of years in this software verification competition. So this is great, but then when we, for example, try to install MOPSA, so there is some package manager to do that, of course, but you can see we have plenty of OCaml dependencies in these white boxes and system dependencies in these gray boxes. And if you take the transitive closure, well, plenty of things could happen. So I think there are sometimes good reasons to try, you want to try out some software without the hassle of installing all those packages on your laptop. So TryMopsa is a way to do that. It's a scaled-down version of MOPSA that runs purely in web browsers. So you don't have to perform any installation here. And it will support the core features of MOPSA. I'll get back to that in a minute. And it features a responsive interface, meaning that you can even try to use it on your smartphone if you'd like. And I'd say it scales in the number of users because it's running purely on the client side, so you don't have to, the server doesn't do any computations there, so it's way more scalable than other approaches. And I'm also here to, I hope, entice you to use it for onboarding or teaching about static analysis. So in the remainder of the talk, I'll go a bit into the technicalities of how we achieved this creation of TryMopsa. Then we'll go for a demo, if all goes well, and then I'll discuss a bit the implementation. So just before we go into the how we compiled basically Mopsa to JavaScript, let's see a bit how Mopsa works. So Mopsa is a static program analyzer, so it needs a program to work on. We analyze different languages, so I already mentioned Python and C. We also have a language called Universal, which is, let's say, a toy imperative language working on mathematical integers. There are two other things the user can provide to Mopsa to customize its behavior. So one is a configuration, which is the composition of abstract domains you want to use for your analysis. And the second is command line options to, for example, tweak the fixed point engine and that kind of stuff. So now that we have all these inputs, the top level analysis will be able to do its work. So in there are iterators, partitioning, interval abstraction, congruences, string abstractions, relational domains, and all this so does its computation, and there are different ways that Mopsa interacts with the user. So we have three different modes. One is called the automatic mode, so this is the most classical one. You just trigger the analysis, wait for the computation to finish, and then check the results, which is like a list of potential alarms. There is something we call the interactive engine, which is basically a GDB interface, but working on the abstract state. So you can basically step through the abstract computations to look at the abstract state at each program point and see a bit more how the analysis is working. And then we have this DAP mode, which is basically the interactive engine, but working through the debug adapter protocol supported by some IDEs. So now to make all of Mopsa work in a browser, basically we try to compile everything to JavaScript. So Mopsa is mainly written in OCaml, and there is a compiler called GS of OCaml that will do most of the work. So with this, we get basically quite a few components already. And then there are the issues coming up. So for the parsing, our front end uses mainly this Menier library for parsing. So this works for Python and Universal. For the C parsing, we connect to libclang, and it's way too much manual work to make this work in TryMopsa for now. So for now, TryMopsa only supports Universal and Python as front end. The issue being that there are some ways to compile Clang to WebAssembly and that kind of stuff, but interfacing this with the GS of OCaml code is something you'll have to discuss with the OCaml Pro people. Another thing is we use arbitrary precision integer arithmetic. So this is the zarif library, which is also written in C, but hopefully there are some an equivalent stubbed version in JavaScript that is already available. So we just do a drop-in replacement here. So we get back intervals and congruences. Yay. And then there are relational domains. So Apron, for example, provides polyhedra and octagons to Mopsa. And this is all written in C, so there's not much hope being able to run them as is. But hopefully there's been some work on verified polyhedra. And what's nice about them, for me at least, is that there are versions that are written in pure OCaml, so I can just compile them to JavaScript. I don't think it was the original intent of the people in Grenoble, but it's very nice for me. I can now have polyhedra in the browser. I'm really happy about that. And then floating point. So we have this interval abstraction for floating point that relies on setting rounding modes to be sound. And this is not supported this setting of rounding modes is not supported by neither JavaScript nor WebAssembly, so for now we don't have any floating point intervals working in TryMopsa. So this was a bit what TryMopsa supports, and then I'm going to explain a bit how it interacts with the web page. So we have two components. One is the top level that will handle user interactions, the rendering of the web page and everything. We use something called the ACE editor so that people can edit their program in the web page with some tweaks to do some custom highlighting. And so Mopsa uses lots of ANSI escape codes to render some text output. So we have some customized things here to render that into the web page. We also handle dynamic option generation because in Mopsa, if you, for example, enable a new abstract domains, it can trigger, it can create new options that you can customize. So we have to regenerate them every time the configuration is customized. And then basically this, so once the user is done setting their options and program, will trigger the computation in another thread called a web worker. So this is independent, so it won't freeze the rendering of the web page, for example. And this web worker will actually do the computation. And it will intercept basically what Mopsa is reading from the standard input or outputting to the standard output and forward them to the top level so the top level can render them or ask the user for input. And we also rely on something called virtual file systems to embed our stubs, for example, for the Python libraries and the different configurations we provide as examples. So one thing I've mentioned before is we have this interactive engine that works well in command line output, but this is like we're in that setting where we're having some kind of synchronous blocking interaction loop as a REPL. And this is quite difficult to implement in a web browser that usually require asynchronous interfaces. So here we rely on a library called SyncMessage that hacks some low-level browser APIs I won't talk to you about and enables synchronous communications. So now I'll get to a demo in a second, but before that I'll explain to you the program we'll consider for the analysis. So this is our universal language, so this toy imperative language. We start by creating a string A, and then an integer I is initialized to 1, and then we do this while loop until basically the character A plus the integer I is less than the character Z. We randomly stop the loop whenever we'd like, or whenever the randomness would like. And then we concatenate our string S with a new character. So for example, if I equals 2, this will be just string B. And we increment I. So basically what this does is it computes a string S, which is either A or AB or ABC or the whole concatenated lowercase alphabet. And one assertion we may want to prove is that for any, basically any index, the character at any index minus the character A is strictly less than the size. So sanity check, for example, if you take C minus A in characters in ASCII codes will be 2, and this will be strictly less than 3. So this seems good. So let's go into this demo. You can also play with TryMop sites available there, and let's try that. So if you go to the web page, you'll basically land on this page. So you can see that we have this code editor here. The analysis results will be displayed there. Then we have these configurations you can edit for the different abstract domains you use, and the options, we'll get back to those in a minute. So here I'm going to trigger a first analysis with, so you see we have different abstract domains. I'm not going to comment every one of them, but we have a loop iterator, for example, we do some function inlining, and we have an abstraction of strings that will just track their length, and the numerical part is just integers. And this is just the program that I've shown you. So let's trigger the analysis. OK, it works. Good. So here, the analysis succeeds, and we have two alarms. One is we are unable to prove that this is a valid subscript access, and the other is we're currently unable to prove this assertion. So let's try to investigate a bit why this is. And to do that, let's try this interactive engine I've talked to you about. So now you have like this GDB-like thing working. So you can put breakpoints. So for example, we'll try to understand what's going on here in our fixed point iteration. So we put a breakpoint, and we go there. And then we can, for example, print the abstract values related to our string and our integer. So for the first step, we have a loop unrolling, so nothing interesting there. Let's continue. Second step will be the first iteration of the fixed point. Not that interesting either. So let's go to the next one. And here, basically, so one widening has been done. So you see that I has been generalized to the interval 225, but the length of the string is apparently just greater than 2, but not bounded anymore. So this is the source of the imprecision of one of the two alarms we had, because we don't really know here the length of the string. And here it's mainly because our interval analysis is unable to relate those two variables. So to change that, we can enable, we can add our relational domain. So this will be polyhedra based on this verified polyhedra library. And we can run the analysis again. So let's go here and print S and I. And now you see, OK, let's do one more iteration, sorry. And now you see that we've been able to infer that I is equal to the length of the string S. So we're happy. It's a bit better, but if we continue the analysis, so we only have one alarm now. So we've improved our results, but we haven't been able to prove the safety of assertion here. And to do that, basically, currently on our analysis reasons only on the length of the string, but you see this assertion here needs us to also reason on the contents of the string. So here we're going to do some kind of, let's say, container abstraction, and we want, so since our string can be of arbitrary size, we don't want to abstract every different character of the string in a different, for example, variable. So what we'll do is something called a smashing abstraction. It usually works on, for example, arrays of integers. So you have this array, and you'll say, OK, these elements of this array are just contained into this interval 1, 9. And here we just add this layer of, so we're using string, but we'll just encode them as ASCII characters. So if you take the VMCAI string, for example, it will be represented in this contents variable, numerical one, between 97, so this is the ASCII encoding for letter A, to 118, which is the ASCII encoding for letter V. So we can now trigger this into so we can trigger this string summarization abstract domain combined with our string length domain. I'm going also to disable the interactive engine and just print the abstract state here. And now you can see that, so we've been able, so this equality was already here before, but now we also have an inequality between so the contents of the ASCII codes of the string and 96 plus I. So, and this is basically equivalent if you, well, if you take these two, this is equivalent to this assertion. So the program is proved correct. And I'm hoping that I've shown you a few interesting things about the relational analysis that MOPSI can perform. So now let me discuss a few points about the implementation. So MOPSI is around 87,000 lines of code. Try MOPSI is way smaller compared to that, so there's a few thousand lines of code for the web page. There is this top level and worker separation of work that is around 100 lines of OCaml code. We have this new VPL binding for our relational domain. And all this compiled and optimized by GS of OCaml is 3.1 megabytes, so that's not too heavy to load in a web page, I think, by today's standard, at least. And one interesting thing I find about this is we have no breaking changes with MOPSI, so I think it's really, we can have this. I'm hoping that we can maintain this for quite some time. Regarding performance, so I've tried to compare the binary execution of MOPSI on my laptop to the Firefox execution through some customized testing framework I'll present just after. And so these are really toy examples, and they are here just for demonstration purposes. But what we can see is, so we have 5 times slowdown compared to the native binary, but I think that in this context, the raw performance is not a priority. You really want just to show some examples or play for some examples for students, so that could be fine, and it's still reasonable. And then I try to assess the browser compatibility, because depending on your browser size or browser engine, it can be quite a mess. So here I use something called the Playwright framework, which is open source. And we wrote a few conformance tests, so to ensure that the different features of the analyzer work as expected. And they run on 3 desktop browsers, so I think Chrome, Firefox, and Safari, and 2 mobile browsers, so I'd say Chrome and Firefox, in 2 viewports, so either landscape or portrait. And so this enabled us to identify and fix several rendering issues, especially on mobile. And we also have additional tests to ensure that the toy programs we provide in the interface run in most of the configurations we provide. And just to give you an idea of how Playwright works in UI mode, so you can see here, this is basically the rendering of the test instructions that are written in TypeScript, and here there's like a nice rendering of step-by-step of the test. So I find it's quite fancy interface, at least for a static analysis person like me. So before concluding, I'll just want to mention a few different things about related work. So one is, there's been ways to try analysis before, and they were mainly working on the server side. So there is interproc, banal, and Katerina's function. So they need less adaptation, because you basically run your binary the binary of your analysis on the server side. But this creates, I think, maintenance and security issues. And case in point, I think only one of those 3 currently works right now. On client side, there's been some, quite a few developments thanks to GS of OCaml, or at least for the 2. So Chow Prolog is not in GS of OCaml, but so the Salto analyzer for OCaml by Benoit mostly. It has, you can try it through a web interface, and there is also a Binsec tutorial that was given at PLDI, but also yesterday, I think, that has some JavaScript versions where you can try things directly embedded in the tutorial page. And I think TryMopSci is the only one currently supporting relational domains and this interactive user input for the interactive engine, for example. So in Venice, there is this library for static analysis that Luca Negrini and others use also to teach. So there, students have to implement some new analysis. So TryMopSci is a different use case. I think we just want students to be able to play with analysis, understand how they work, but they won't be able to edit the actual implementation in the TryMopSci web page. And there's been works on interaction with IDEs and also different combinations between concrete and abstract debuggers by other groups. And with that, so I've presented to you TryMopsa. This is a pure JavaScript version of Mopsa, supporting the core features of Mopsa, mainly relational domains and this abstract debugger. It works on smartphones and desktops alike, and I think it's really useful for demo or lightweight teaching purposes when you want students to play with different analysis of some toy imperative or Python programs. And feel free to use it here. With that, thank you for listening. I'll be glad to take any questions that you may have.
Are there any questions for Raphael?
So thank you for the talk. So I really like this this way of having something that allows the students to really have like this very nice experience. And have you tried to work with some students, or do you have some user experience reports? What was easy to do? What was not easy to do?
So I don't have a cohort of students to try it on right now, but I know Francesco Ranzato used it a bit in his course this year. He previously used Interproc, and I think he's mostly satisfied with it. I still have to see with him. One thing we don't do that Interproc did was output program invariants per program point. State invariants per program point. We don't have a good way to show this in the interface right now. We can like show it here at specific points with these prints, but otherwise, it's a bit difficult to do, especially with this fully context-sensitive approaches of functions we do. So I'm not sure how to handle this specific feature. But apart from that, it seemed to be working fine. And I don't have a larger cohort to try it on. But I'd be happy if you try it. Let me know.
Thanks for the talk. Do you think it would be feasible to reuse your web interface so that other tools could also have a very nice interface like that? And how easy would that be?
With a bit of cleaning, I think it could be done, yes. For now, I haven't like tried to generalize the interface enough, but so it's ugly in a way, but practical in another, that basically the web worker intercepts these standard input and outputs and then sends them to the top level. And I think this is general enough that other analyzer can just step right there. So we can try.
Okay, there's another question there.
Thank you for the talk. You mentioned that you don't have C because LeapClang doesn't work on. I think that CompCert has a C parser, like a minier parser for C in the GPL version.
Yeah. So yeah, they do. So I haven't tried to connect it, and the main issue was my understanding of this front end is they probably need the preprocessed source code, so they don't handle. I'm not sure about what I'm saying here, so if someone more familiar with CompCert knows, feel free to interrupt. But I think they don't handle includes and all that, so if we use some like standard library things, it's going to be complicated, and I don't want to go there. Because I think if you don't have like the standard inputs and that kind of stuff, it's beside the point of C analysis.
Okay, any more questions? If not, let's thank Raphael once more.
Thank you.
So now we have a break. Could I just ask the speakers and the session chair for the next session just to meet up here to make sure that everything is ready for
welcome to the second session of the day. The first speaker of the session is Michael Schwarz from the University of Singapore, and he's going to tell us about data race detection in the Goblin static analyzer.
Okay, so thank you for the kind introduction. So indeed, today I'll be talking about data race detection by digest-driven abstract interpretation. Throughout this talk, we'll be looking at this example a couple of times, so it may be worth spending some time looking at it. So it's a very simple example program. You see that we have two threads, namely this main thread and then another thread T1. And we have a set of mutexes. In this case, we have this mutex A. And we can initialize this mutex, and we can lock and unlock the mutex. And we also have global variables. For instance, here we have this global variable G. And what this program does is first, while no threads are created, it assigns a value to this G. Then it dynamically creates a second thread, namely this thread T1. The first thread then locks this mutex A, assigns a value to G, and then unlocks the mutex again, whereas this other newly created thread also locks the mutex, assigns a value of 12, and then unlocks the mutex. Now, in one of the questions that we might ask ourselves about this program is there a data race in this program? And the classical definition of data race is you say that two accesses in a program race, if at least one of these accesses are right, if they access the same data, and if they can somehow happen at the same time. And in this work, we're focusing on the last aspect of this. So we're deciding whether two accesses can potentially happen at the same time. So let's unpack the title maybe a little bit. We're saying data race detection by digest-driven abstract interpretation. Now this is VMCAI, so I won't spend too much time explaining what abstract interpretation is, but just briefly in case someone is not familiar. So it's a technique that was proposed by Patrick and Radia Couzeau in the 70s, and it works by systematically over-approximating the concrete program behavior. And then if you can show that your over-approximation of the program behavior does not admit the bug or the problem, then your actual all concrete program executions will be safe too. Now, when you apply abstract interpretation naively to multi-threaded programs, you immediately run into a state explosion problem. So this does not really work. So what you need to do is you need to be a little bit smarter in some way, but also less ambitious in another way. Namely, what you want to do is you want to do something that's called thread modular abstract interpretation, where you try to analyze each of the threads that you have in your system in isolation as much as possible. And this is not completely possible because different threads in your system usually tend to interact in some way. But for this interaction, you decide to go for a quite coarse abstraction of this interaction, so coarse over approximation. So if you think about value analysis, an example may be that you say, okay, for all of these global variables, I just assume that any read that I have in my system can read any of the values that were written at any point. So this is thread modular abstract interpretation, and what this gives you is something that's usually quite scalable, but also often quite imprecise. And this is then the point where we come to digest-driven abstract interpretation. And we have observed that there's a lot of ways that you can improve the precision of these thread modular abstract interpretations. And what they usually have in common is that you tend to preserve some part of the history. So you have some history abstraction, and then you take this into account to decide which interactions are actually feasible. So if you think about, for example, about a value analysis, you may say, okay, a thread cannot actually read a value that is written by another thread, which can definitely not have been started yet. Or another instance of this is that a thread cannot read older values that it has written itself if it has definitely overwritten them in the meantime. And then digest-driven abstract interpretation is a principled way of designing these history abstractions. And the nice property that you get is that you sort of you get a separation of concerns in some sense. So you have an analysis that you prove sound, and then you have some requirements on your digests that you need to prove, so on your history abstraction. And the result here is that these compose nicely. So basically, if you come up with your new favorite analysis that aims to be more precise by taking yet another aspect of the history into account, you don't need to start proving your analysis soundness from scratch as long as it follows this principle. So this is some result from 2023. And you can think of these digests in some way as a type of concurrency sensitivity, because they specify which aspects of the thread interactions you want to track and what you want to abstract away. So you can say, oh, in some way it is similar to flow sensitivity, context sensitivity, and all of these other types of sensitivities that people have proposed in sequential analyses. Another helpful way to think about it, especially if you're an abstract interpretation person, is you can see these digests as a generalization of this trace partitioning technique that Xavier Rival and others proposed to a multi-threaded setting. What are examples of such digests? Examples of, for example, are computing the set of held mutexes, where at every program point you track which mutexes you have. Another example would be an analysis of dynamically created thread IDs, where you try to compute thread IDs and maybe also try to determine which threads are unique, so which type of threads are in the system where you only have one instance of them. So this is an example of a very simple digest where I'm computing some type of thread ID. And here I have two different thread IDs. So basically I have a thread ID for the main thread as long as it is single threaded. So as long as it has not created any other threads, we give it this thread ID st main. Then we have empty main, which is also for the main thread, but basically that's its thread ID as soon as it starts creating any other threads. And then all of the other threads, we don't distinguish them. We just say, okay, they fall into this category of other. Now, if I look at our example program again, and I do an abstract interpretation that uses this digest, then I would, for every program point, also have the digest information for it. And in this case, it will always be st main until the main thread goes in and for the first time creates another thread. Then it has this thread ID empty main. And then the newly created thread, this t1, will always have this thread ID empty other. And now if I think back to our value analysis that you might want to do, you might want to ask the questions such as, can this variable r that reads the value of g, can the value of this be 12 after the value has been read into r? And the question here then becomes, is st main in some sense, it does not seem to be compatible. We're back, okay. So the question becomes, is st main compatible with empty other? So this is the question that you might ask yourself here. And if you think about it, so when we are doing these digests to improve the precision of value analysis, we're somehow asking these questions, are two digest compatible? And when we're thinking about data race detection, and especially this aspect of can the access happen concurrently, then our question becomes, can two accesses possibly happen in parallel? And if I squint a little, then I can turn this data question into the question of, can two accesses possibly happen in parallel given their associated digests? And then I see that actually there is some type of connection here. So in both cases, I'm asking questions about these digests. And this was the starting point for this work that I'm presenting here. We basically wanted to reuse all of this machinery that we have for improving value analysis to answer questions about whether there may be races. So the contributions in the paper, there's a first part that deals mainly with the concrete semantics. So to have nice proofs of our analysis, we have a concrete semantics that is also thread modular, and we call this local trace semantics. And for this question of races had not been studied yet. So we provide the definition of what it means to be racy in this local trace semantics. One is quite intuitive. The other one is a bit less intuitive, but in some sense it's nicer because, as we'll see later, it lends itself more easily to abstractions. And in the paper, we then show these two definitions of races in the local trace semantics equivalent. What we'll focus on this talk a little bit more is how we are actually using these digests for data race detection. So we will show a technique how you can use any digest that you have to answer questions about which accesses can happen in parallel. We will also see that this generic definition is not always the best one that you can hope for, and we'll provide some bespoke definitions. We will cover the algorithm for digest-driven data race detection that's used inside of the Goblin tool. And lastly, I'll also briefly talk about our experimental evaluation that we did of different digests on the SVComp benchmark suite. So for the first aspect, let's take a look at our example program again. And when we think back to our value analysis, we would say, or we can say that some things are not compatible and others are. So for example, if a thread is st main, then it would only be able to read other values that were written by the main thread. So this is one of the conditions that we can give. And the other one is empty main or empty other can read any other values, can also read things that were written while the thread was potentially, or while the program was still potentially single-threaded. And one way to write this down is in this way here. So what we're doing here, don't be scared off by the syntax, but basically what this says is I'm computing the successor digest given the digest of the thread that's reading and the digest of the thread that performed the writing. And here what I'm saying, well, if I am the main thread and I am trying to read something from some other thread that is not the main thread, this is not possible. So this cannot happen. And then I say here, the set of successor digests is empty. And in the other instances, the successor digest will simply be the digest of the first thread. Because if I am the main thread and I read from some other thread in the program, this doesn't change my thread ID. So this, we have just to introduce the notation. And then let's see how we can get from this to actually the races. So if let's consider a data race between two accesses. And let's say these two accesses have the associated digests A0 and A1. And then the access with the digest A1 can be ordered such that it happens before the access with the digest A0 because they are racy, so they are unordered. And in this case, if I'm reading with the digest A0, or if the thing with the digest A0 is a read, and the thing with the digest A1 is a write, then the read can read the value that was written by this writer. So basically what I conclude from this is I can say if there's two accesses with digest A0 and A1 and they are racy, then in this abstraction here, I say that these digests must be compatible. And from this we can conclude that these digests cannot, or two accesses with digest A0 and A1 cannot race if they are incompatible in this digest world. And now because we have chosen A1 and A0 arbitrarily in the beginning, we can also flip those around. So basically what I can say is two accesses can only ever race with each other if the digests are compatible in both directions. And then this leads us to the definition of this predicate, which is supposed to answer exactly these questions. So I have two accesses with digest A0 and A1, and I want to say, can they possibly happen concurrently? And we write it down like this. So we have this predicate, we give it two digests, and then this predicate will either return false, which says the accesses with these digests can never race or can never happen concurrently, or it will return top, which says, okay, they may not race. So returning top instead of true here is a deliberate choice because we have done an abstraction before. So usually we are not able to say that they will definitely race. We can just say, okay, we don't have enough information to exclude that they will race, which is why we have this top here. Now, we can define this predicate in a generic way by using this insight that we just had before from this bidirectional digest compatibility. So we can say if the digests are not bidirectionally compatible, then we know that there will be no race. So this is this definition here. And if they are bidirectionally compatible, then we don't know anything. Then we show that this definition is actually sound for any digests. And the way this works is that the bidirectional trace compatibility, which we show to be equivalent to the intuitive definition of a data race, implies the bidirectional digest compatibility by the construction of the digests. So this is a proof that you might want to read up in the paper. What this gives us is a way to automatically derive from any digest, a way to check for data races. And the nice thing is this doesn't come with any additional proof obligations. So if I have a digest that is admissible, that I can use in my analysis, then I can also use it to check for data races without having to prove anything else. So let's take a look at our example. So recall we had this program with the single-threaded, with the thread ID digest. And what I've done here is I have basically inlined these definitions that we had given earlier for the trace compatibility. And what this now says is the two accesses do not race if the first thread is the single-threaded, if the thread is single-threaded and in main, then it will not race with anything that is not single-threaded in main. And it also, yeah, so this is but both directions. So this we can already use to exclude some of the races. So for example, we might be able to exclude the race between this axis here, where we set G to 0, and this axis here, where we set G to 12. However, this is also an example of why this generic definition is not always precise enough. Consider, for example, this case here. The single-threaded main thread, single-threaded main thread, according to our predicate here, races with itself, which in some sense is logical that our predicate would give us this answer, because we constructed it from answering questions about, can we read values that were written by this thread? And yes, of course, I can read values that were written by myself before. So this here will give us top, and the same for the multi-threaded, for the main thread in multi-threaded mode. We will also say that it might potentially race with itself. So this is why this definition here is not completely satisfactory yet. And what we actually want is we want to give a dedicated definition here that exploits all the information that we have in our thread ID domain. And for example, this might say the first part says that axes with thread ID st main are never involved in any races. And the last part says that if both axes happen by the main thread but already in multi-threaded mode, then they can also not be racy. This is a dedicated definition that captures more of the things we want to capture. The downside here is that, of course, now I will have a manual proof obligation. So now I will have to show that this actually implies that there will be no races. Let's take a look at another example. So this is the log set analysis and the log set digest. And there probably people will agree that if the log sets that you hold at the two axes have a non-empty intersection, then they will not race, because they're somehow protected by these mutexes. And this is what the predicate here gives. And this is once again an instance of this dedicated definitions that we have. And then we might want to actually show that this definition is sound for the log set digest, and I'll give you a flavor of what a proof of this would look like. And the proof here would look like that I say two axes holding, if you have two axes that hold a common log, let's call this log A, for example, they are ordered with respect to each other by the locking and unlocking operations for this mutex A. And then what you have is that one axis sequence must happen before the other axis sequence, and I cannot flip them around, and therefore they are not bidirectionally trace compatible. So this is the type of argument that you need to make here when you want to show one of these custom predicates. Now, something that will also immediately be obvious to an abstract interpretation audience is we have several of these things. Let's maybe try to combine them, and this here is an easy way to combine them. You can say, okay, if one of the digests that I have can exclude that they can race, that this is good enough. So it suffices if one digest can say this. And if both say, I don't know, then we also need to say, I don't know. This, in some sense, is a bit like an open product. The nice thing about this definition here is that it's once again sound by construction. And then the reviewers already asked, okay, but this is sort of boring. Why don't you do a reduced product? And yes, this is a good point. We can also do a reduced product where we try to exploit more of the information contained in the digest, and maybe also use the information from one digest combined with the other digest to finally conclude that there's no races. The downside with this is, whereas for the open product it was somehow sound by construction, for this reduced product we need to actually make a proof. But it's actually also helpful, and we do use it, for example, in the Goblin system. We use it when we are combining thread ID information with set of must join threads. Okay, so then let's maybe show what our data race detection algorithm in Goblin actually does. So this here is our typical starting step of an abstract interpretation. We construct our constraint system. We do this by supplying the program, the digest, and then your transfer function of usual abstract interpretation. This gives you a constraint system. To this, we add an additional unknown where we will accumulate all of the accesses to a given global. So we have an extra unknown RG, and there we collect information about all accesses. Then we give it to a fixed point solver, whichever fixed point solver you like. And what this fixed point solver at the end gives us is a solution. And then we iterate over all of the accesses that we have accumulated. And basically for all of the accesses, we check, well, is one of them a right? This is this line down here. And if at least one of them is a right, and our nice predicates cannot exclude that they may race, then we actually report the race to the user. Let's take a look at our example again. So during this accumulation of accesses, we may find that we have an access in this line 2, which is a right, and then we have the digest information that's associated with this, so main thread in single-threaded mode and no log set. And we do the same for this other access in line 6 and the access in the other thread. And after we have computed the result here, we then go in and try to check pairwise whether these things may race. And we first start off with this st main, and we check whether it may race with itself. Now we have refined the definition of this predicate, so here we'll say, okay, main will not race with anything. So for all of them, we will find that they will not race. So this access cannot be involved in any data races. Then we continue with empty main. For empty main, we also said it does not race with itself. So this is also safe. Then when we consider this pair here, we see that the thread IDs are not enough to exclude that they may race. However, here I have a non-empty intersection of the log set. So those two are also safe. So is this one. And then lastly, I consider these accesses empty other. And there I find that the thread IDs, once again, don't suffice to exclude the race. But we have, once again, this non-empty log set intersection. So then I would conclude for our fabulous program here that is actually race-free. Now we have experimentally evaluated these things within the Goblin static analyzer. And actually this digest-driven abstract interpretation provides the semantical foundation in some sense for what this Goblin system has been doing for a long time. And this Goblin system actually was winner in the data race categories of SVComp in 2021, 2023, and 2024. Now we look at 2025, which it didn't quite win, but it's the most recent one. So the benchmark set in SVComp consists of about 800 race-free programs and about 250 racy programs. And it's a mixture of regression tests and tasks that are extracted from real-world software. If you look at the tools that competed and got a significant score in this category, then we see that Goblin here is the only tool that did not produce any false negatives, and also the overall number produced by the tool is quite impressive. And this cooperating tool here actually also incorporates Goblin as one of its components, so this is not quite a fair competition. So the question that we then asked ourselves, okay, which of these digests that we have in the Goblin system are actually responsible for these results? And we have the following digests. We have this log set digest that we've seen before, extended with support for reader-writer logs. We have this TF, is the simple thread IDs that we have just seen. We also have some more advanced thread IDs, and we also have some analysis of mass joined threads. And then we have a bunch of things that came out of specific papers. And then when we evaluated the results, we found that for 15 tools, we needed none of the digests to show that they were race-free. So basically, these tests only contain atomic variables. So they are not that interesting. On the other hand, we saw that each of the individual digests, they sometimes move the needle a little bit. But to actually get impressive results, it is the combination of both of these things. So the conclusion is here that for the tasks that you have in SVComp, you need a combination of log set reasoning and thread reasoning to show race freedom. And the last thing is maybe also a bit depressing. If you look here, these very specialized techniques that colleagues of mine came up for their papers, they don't matter so much on these benchmarks anymore. So we already get 681 without these specialized things, and then they only add a few more. So what we have seen here is we have seen the definitions of race for this local trace semantics. We have seen a framework to check for races using this digest-driven abstract interpretation. We have seen how we can automatically derive this predicate to basically benefit from any digest that your analysis implementers have provided. And we have seen that sometimes you might want to do bespoke definitions. And we've also seen a little bit of the experimental evaluation on this SVComp benchmark set. And with this, I'd like to thank you for your attention, and I look forward to any questions you may have.
All right, we have 5 minutes for questions. Any question?
So thank you for your talk. I was wondering, so you showed that the more the digest, the better the precision. How expensive is the combination of all those?
So this is a very good question, and we have to admit to our shame here, we did not evaluate how expensive these combinations were. So in our experiments, what we did is we basically always enabled the digest, and then only for the post-processing we turned some of them off to see what their impact was. Now potentially they can be somewhat expensive because what we get is an abstract interpretation that is sensitive in this digest. So if you imagine a digest that has 10,000 disjoint values and you encounter all of the program points with all 10,000 values, then you get an immediate blow up. In practice, we have not seen this blow up, and I think for these tasks, I don't have the exact number in mind, but I think none of the tasks took longer than 30 seconds to analyze. Does that answer your question?
Another question, maybe? Don't be shy. So I have one.
Sure.
Can you tell us more about the assumptions on the memory model that you made so that your analysis is sound?
Yes. So this is a very good question. So our assumption for the memory model, so there's two parts to this question. So we have a hosting abstract interpreter, and this hosting abstract interpreter, you can confine it, you can configure it with different types of analyses. So we have non-relational analyses, and for these, we have shown it to be sound for sequential consistency, but it should also be sound for some weaker types of memory, because basically our abstraction is coarse enough in some sense. If we go towards, you can also enable relational abstract domains, and these relational abstract domains also, so they sometimes infer non-reachability, and this leaks into the race detection thing. And because sometimes a program point, your base analysis will say, oh, it's completely unreachable, but this is actually under the assumption of sequential consistency. So if you configure it with relational domains, then you actually need the sequential consistency. Then for weaker memory models, we will be unsound.
We have some time for one quick question. Well, if there's none, then we can thank Michael again. Let's wait 30 seconds for the last people to show up.
Okay.
The second talk of this session is going to be given by Naim Moussaoui Remil from INRIA. and Naim is going to talk about termination resilience static analysis.
Thank you. So, hi everyone, thank you to be there for my presentation. Today I will present the work I did under the supervision of my PhD advisor, Katarina Urban, and which is a static analysis for a new property called termination resilience. So let's introduce this static analysis through an example. We'll use through this talk an example, which is a function foo taking in input a variable x. Then it's assigning to z the value 10. And then we encounter a if-else block. Inside the if block, we have a while loop. While z is positive, it decreases the value of z by the value of x. And in the else block, while z is greater or equal than x, it first assigns to c a random integer from -2 to 1, and it increases the value of z by the value that has been generated. The if condition is now some dots. Let's consider it as non-determinism choice. Both blocks are possible. And in the context of termination verification or non-termination bug finding, we have a problem here because the both of the loop may diverge. The first one may diverge if the input value x is negative, less or equal than 0. And the second one also, if, for instance, all the random integer that has been generated are greater or equal than 0, because for the first case, the value of z will always increase, so it will always, the condition will always hold, and for the second loop, it's the same. So the question that we want to ask here in our work is which non-termination alarm is more critical? And to distinguish between them, we'll say that we want to be more cautious about the input value. We'll take somehow an adversarial setting and say that this one should not be trusted. And we can see that the first loop, the condition to diverge only depend on x, and just the input of this function can enforce a non-termination of the program. In our work, we formalized it as a property that we call robust non-termination, attesting that a non-termination bug is robust and then more critical. More or less formally, it is defined as the fact that there exist some inputs such that for all internal choices of the program diverge. Here, the internal choices correspond either to a deterministic statement such that the assignment to z, or the random integer assignment here. Our goal is to get rid of these critical bugs and to define and to do a verification of program attesting that there are not such critical bugs only depending on the input. And so the definition of the property that we want to verify is simply the negation of the robust non-termination, which we call termination resilience, and is again more or less formally defined as the fact that for all input there exists an internal choice of the program. There exists potentially multiple internal choices leading to the termination of the program. And this is the case for the second loop that we have seen. If, for example, the sequence of random integers that are generated are strictly negative, for a long enough sequence of iteration, at some point we'll exit the loop and terminate. And in our context, we'll say that this loop is safe because our property holds. You can think about this property as a termination property, but where we refine the notion of non-determinism inside our program. The non-determinism that is induced by the input value, we want to treat it as a mnemonic non-determinism. And for all other non-determinism induced by the statement of the program, we want to treat it angelically. And my contribution here, with this property defined, is a static analysis for this property. So as usual, in an abstract interpretation-based static analysis and in static analysis, we want to define the semantic of the property to verify in a concrete point of view. And just here, I give you a global view on what we want to do. We want to start from the end of the program here with some final state that are depicted in purple. From there, we are sure that the program terminates and hence the termination resilience property hold. And we want to compute backwards through the execution steps how many execution steps are needed to terminate. The semantic, more precisely, is defined through a fixed point and defined a ranking function from program states to a world order set. Here we only use natural numbers. And as I said, we start from the final state with the value 0. For all other states now, they are undefined. They are not inside the domain of definition of our function. And then we try to go backwards through the predecessors of the defined states to find how to count how many number of steps are needed. So in the first step here, the possible predecessor are this state and this state. For the top one, 2 branches are possible through blue transition. Here, the blue transition represents the internal choices that in the formalism I call regular transition. And as I said, and as we saw in the property, we want to treat it angelically, and so only 1 branches is needed, but here, in any case, both lead to a final state, so we add it in the domain of definition. Here, we needed 0 step to terminate, so trivially, logically, we need 1 here. But for the branches at the bottom, 1 lead to an infinite execution. But as it's a regular transition, one where we can allow at least 1 transition toward a terminating state, we can add this state in the domain of definition. So you can see the link between the exist in the definition and the fact that here you take the infimum and you use the predicate transformer of the pre. Just to show you that we also consider just deterministic transition as regular, we can do 1 more step and add this program state in the definition with the value 2. We could not add the first state here because the branches were from where the transition to go toward a defined state are only input transition that I depicted in red, and they go to this defined state, but not to this one. So there is a possibility to diverge here. But if I continue, at some point, all the possible transition with the input transition leads to a defined state, meaning that all the choices through input transition are safe because we always terminate. And it's formalized through the fact that here we use the predicate transformer of the pre-tilde defined through a for all, and there was the exist here. And we use the supremum with the same idea of taking the link between a for all and a supremum as it's used usually in mathematics. So this semantics is sounding complete for the verification of our property, termination resilience. But as usual, it's not computable if you in the general setting, and we want to define an abstract semantic for that. This abstract semantic relies on an abstract domain that compute piecewise defined ranking function. And the soundness criterion here is interesting. We want to under-approximate the domain of definition of the concrete ranking function on the left and over-approximate its value, meaning that we infer sufficient condition for termination resilience, plus we over-approximate the number of steps before termination resilience. Internally, it's represented as a decision tree. The plot on the right represents the function defined when the value of x is negative and with the value 2. It's exactly how it's represented for the decision tree. Here, what we have, if the condition hold, we look at the leaf on the left, and we have a bottom. The bottom represents the approximation, so it may mean that in the concrete, it may mean that in the concrete we have robust interpretation, but we don't know, so we'll keep it undefined. And on the left, we have a value 2, meaning that in at most 2 steps, the termination of program happen. With this abstract domain, we do a static analysis, and as for the concrete, we start from the end of the program and we go backward with the value 0. We have transfer function to handle if condition, where here, for example, it filters the domain of the program and reduce it and increase at each step the value of the function. We have an assignment transfer function that can, for example, here extend the domain. And for the while loop, we do some iteration, and we have a widening operator that do some extrapolation and try to predict the global value of the ranking function. So my goal here is to give you some key idea on how we do the static analysis. And I will directly jump inside some iteration of the analysis where at some point here at the control point 9, after the evaluation of the transfer function for this assignment, we obtain a decision tree telling you that if z plus c minus x is positive, you don't say anything, you have a bottom. Otherwise, if the negation of the property holds, you terminate it at most 2 steps. Then, to do the analysis, we go backward, we apply a backward assignment on the tree, and this is where we need to handle some problems. So, to do the backward assignment, we will treat the partition represented by the decision tree independently. So, we want to treat both paths where z plus c minus x is positive and when it's not. So we separate it in 2 trees. One telling you that here we have a bottom, and the nil telling you that here this part of the program state are not considered. Same on the right. The assignment, we apply it on the condition that resolve the inequality that we have on the top, and we obtain the new condition z minus x plus 1 is positive. We do it on the decision tree on the right. We obtain z minus x minus 2 positive, and we increase the value from 2 to 3. From there, we have applied the effect of a random integer assignment on both partitions of the program state. And what we want to do is to join the 2 new results. Before joining them, we need to unify them. It will be simpler. So we unify both trees with to have the same structure and the same path to talk about the same program state directly. And we obtain for the tree on the left this one on top left, and on the right this one on top right. And it's exactly the same trees. It represents exactly the same information if you take a look, because this condition on the left is still implied by this condition here. From there, it's really easy to join. We just have to do an induction on both trees, explore all the passes that are the same, and join the leaves. Let's see how we can do it. So the first 2 leaves that we want to join by the exploration is the bottom and the nil here. As I said, the nil represents the fact that here we do not consider these parts, and it's like when you analyze, for example, it's like having it's like analyzing an if-else block where you can keep the information that you obtain on the other branch if you are sure that the other branch is not reachable. So we keep the bottom, meaning that maybe the property holds, maybe it does not. And everything is the thing that is important is when you join a non-defined leaf and an undefined leaf. Here we have a bottom and a leaf tree that we want to join, meaning that on some precondition you may diverge, but for the other you're sure that you terminate. And as what you want to apply is a transfer function for a random integer, which is an internal choice that you want to trust, you will keep at the end the defined leaves. Whereas when you want to analyze, for example, just a classical termination property, you will have keep the undefined part. And it really shows that the important thing here is that we can use the partition induced by the decision tree and apply smartly some join to keep the information through the static analysis. For the last join, we also keep, as for the first one, the defined value 3. Then I will, to finish the analysis, we obtain this resume tree, meaning that if the condition does not hold, termination resilience happen in 3 steps at most. When we go back towards the condition of the loop, we add it in the tree. Here you have the fact that if the condition of the loop does not hold trivial, you will in 1 step exit the loop. And after some iteration, you obtain 2 trees that you want to widen. And here it's important that you see that here it's defined. It will not have been defined if we have used another joint as the resilience joint I defined. The widening, I will not explain it in detail. It just reuse a previous one for termination and do a linear extrapolation, which give you at the end of the analysis of this loop a fully defined tree, meaning that whatever whatever are the states before the program, before this loop, we are sure that termination resilience hold. So here, what I have shown is the analysis using the random integer, where we are sure that where we are sure that. No, let me rephrase. So here I've shown how to use the resilience join to join partition from where we are sure that termination resilience hold and where it does not. And basically, we want to favor the one where it holds because we are sure that it's an internal choices. What we would like to do is to generalize it and apply it everywhere, some sense. The idea is to having a taint analysis telling you that does this statement depend on an input or not, and then internally you want to apply different join depending on that. The problem that we have here and why we cannot do it, so just maybe let's see the fact that here what we want to do, if the condition is on a random integer, we would like to join the fact that we have an alarm and a safe alarm and a bad alarm with a safe alarm at the beginning of the if block. But the problem is when, for example, you will have the fact that you change the condition with a square positive. Because it's not sound anymore, and because in the concrete execution, the second loop is not reachable anymore. And what we lack to generalize this resilient join here is a feasibility analysis. We want to be sure that it's feasible to reach the second loop such that you can join. Our static analysis has been applied in a prototype analyzer called row function that is a fork of a previous one function. At some point it will be merged, I hope. The prototype is coded in OCaml, not in HTML as depicted in the screen. We only analyze the numerical program with signed integer with the assumption that we do not have any overflow. That's the only assumption that we have on the integer. And we have no assumption on the knowledge of the inputs with regard to the internal choices, in the sense that if you want to modelize the fact that an input has the knowledge of the previous internal choices, you just have to rewrite the program in another order, where the input appears in another orders. To evaluate our approach, we decided to see how we can reduce the number of alarms and attest how many alarms are less critical. So we took many non-terminating benchmarks. We are sure that non-termination happened. And from SVComp, from benchmark of Pulse, and from benchmark of survey by Shi and Hall at FSE on non-termination bug. And all of them, for all of them, we'll run our termination analysis and our termination resilience analysis. Of course, the termination analysis will always raise an alarm, and we have shown that for more than 65% of the termination alarm, we attest them as less critical because termination resilience holds. Just some word about some related works. So our idea came from some work on some safety properties and some runtime error bugs. The first one that we have seen is robust reachability by Giraud et al. The idea is exactly the same as robust non-termination, where they want to check that there exists some value for the input, such that for all internal choices, a buggy location is reachable. The other work is about runtime error, and they take the same approach, but they want to prove that the input cannot either silence or trigger a runtime error. So it's more refined. And here they use the idea of the taint analysis to do that, and we tried to apply it to a liveness property, and we decided to refine it with termination that led to termination resilience. An interesting word that I want to talk about just here is there exists some logic to express such properties, such mechanism. They call it analysis of open programs, where we do not put any distinction between the input are called closed program. And inside this property called alternating time-temporal logic, we can express robust non-termination, termination resilience, and also robust reachability. Just the idea behind it is a CTL property lived with this new notion of distinction between a set of players, in fact, and a set of other players. So some conclusion and future work. Well, there is a break here, I don't know why. So we have seen a way to refine the notion of termination in a new context, where you put some distinction between the input and the internal choices that leads to the property of termination resilience. We define a concrete semantic for that and an abstract semantic with a static analysis. And for future work, what I would like to do is to first work on the analysis of heap manipulating program. As we have seen, we do not have yet a way to analyze heap manipulating program. It's ongoing, and I hope it will be done soon. We have some preliminary on robust non-termination bug finding. In the implementation, it's done in some sense. It has to be formalized. So we have way to infer a robust non-termination bug. And as I mentioned, there are logics that interest me, and I would like to go toward the analysis of the alternating time-temporal logic. That should be okay to do because we can lift the previous CTL analysis to do that. And that's it for me. Thank you.
Thank you. We have plenty of time for questions. Do we have any questions in the audience?
Hey, thanks for the great talk. I was wondering about what's the motivation for termination resilience in the first place? So this differentiation between like angelically handling the random, for example, and yeah, you get the point. Why do we do this differentiation?
Why is the motivation behind the property itself, or why do you want to?
Like, what is this? What real world problem is this expressing? Kind of?
So as I said, it's what it proves. It proves the absence of its negation. That was the goal. Like we say that we should differentiate between some bugs that are more robust, more critical that we want to attest, and we take the approach to verify its absence and not finding the fact that there are robust bugs. And the motivation is that to verify its absence. Then, when you want to apply it more concretely, you have to you can define in different way what are the untrusted input that you want to check. So it can, for instance, be for third-party library that you do not trust, some inputs. And also there is a rooted reason behind that on the static analysis. Because sometimes the transfer function, you don't have a precise way to abstract them. And so you abstract them to top, which in a numerical point of view, so a non-deterministic choice between -infinity plus infinity, if you want. And so that is analyzed as an internal choices, and it can raise some alarm, and you can, for example, discard them because it's only because of the static analysis itself and not the problem. So there are many reasons you have to, many motivations you can apply them in different way, but you discard some robust bug, you're sure that they do not happen, and you can, as we did, filter them.
Okay, thanks.
Other questions?
So can you say a bit more about the relation to CTL, and could you have taken their algorithm and done what you did, or maybe not?
So what I did not say is that as a CTL analysis I mentioned, use a decision tree analysis. So it's a previous one did by Katarina. And so what we could do is rely on the same idea that the decision tree gives you a partition of the states where the CTL property holds. And then you want to reuse the same idea of joining them, depending on what kind of statement you analyze. And so it will, there is, I think, a semantic work to formalize it, to be sure that it works, but it should be okay to lift our idea from termination to the CTL analysis to obtain the alternating time temporal logic analysis. Is it?
Yeah.
To answer your question? But and there is needed to work. It's not straightforward, but that's my intuition.
So thank you for the nice talk. At some point you introduced this nil thing. And I was wondering about if you think of your abstract domain as a lattice, is this a bottom, this nil, or is it not quite a bottom? And what would be the concretization of this nil?
So that's a good question. So it disappear after each algorithm, each transfer. When we apply the abstraction of each transfer function, it can happen during the algorithm, the computation, but then it disappears at the end. So, and that's why it's not part of the lattice or the computation or anything. Yeah, that's it. It's just part of it. It's just that we have a decision tree that represents partition. We split it. We put a nil to say, oh, here it's not represent. You don't have to consider it. You don't have to consider it. And when we join at the end, it disappears. Because as you have seen, it always, the other leaves always win over the nil. And so that's why it's...
Okay, thank you.
Yeah, good question, thank you.
One more question?
So you mentioned as the future work analysis of heap manipulating programs. So could you be somehow more specific? Because that's in general a very big area with like many different approaches. And what do you actually consider like heap manipulating programs, like dynamic data structures or just like some pointer manipulation?
So what we want to do is go step by step. And like right now, what I'm considering is just sequential program where you have pointers. And I want to do a kind of points to analysis lifted with our domain. And that's what I have in mind. And for data structures, maybe we could like rely on like flat data structure directly, but the one that are inductive, no, it's not currently in the project.
And maybe one more question. So do you have some interesting examples for this, for the combination with the analysis of heap manipulating programs? Some nice programs that and the properties that.
So I've sorry. Just with one step, with the step that I have in mind, I would not be able to analyze them. But when I've searched on the CV benchmarks, I have found sums where robust non-termination holds. And they are usually drivers programs. And currently, I could not, even with the step that I have in mind, analyze them. But eventually, at some point, we'll have all the necessary work to analyze them. But it's need a lot of work to scale to have a bigger code-based analysis. But there are some on CVE that we can attest that robust non-termination hold, and we want to distinguish between them and the others.
And do you also consider like going for concurrent programs? Because there are some very interesting like concurrent data structures like skip lists, for example, when you would like to maybe check whether there are some, you want to have some termination guarantee there, right?
So the question is, I would like to, but I think it will not be for a short future.
Yol, let's thank again Naim.
Thank you.
All right. The last talk of the session will be given by Carl Palmskog from KTH, and he's going to tell us about symbolic execution for binary code verification.
Right, so thank you for the introduction. So this is joint work with my colleagues at Uppsala and Intel, and just to point out, a lot of this practical side of the work was done by Andreas during his PhD studies at KTH. So that's there. So before I talk about the kind of binary verification, let me give you some background to this work. We focus on what we usually call unstructured code. This means that you have code that has jumping with labels and so on, and each statement or instruction could have multiple exit points. If you are not careful, then or if you write this manually, you can end up with a can of spaghetti. That's what it's traditionally been called. And you typically don't have a lot of information about typing, or the data is kind of a paucity of types, just machine words, for example. So the thing with unstructured code, it kind of lives as compiler output, for example, and unless you're careful, it could leak, for example, data that you may not want, or have bugs that may not exist at the source code level and so on. It can also be quite difficult to inspect or understand what's going on. So I give this very small example here of an indirect jump where you determine at runtime sort of what function you're calling depending on some value, right? So you're storing the address you're jumping to in some register, and then you're calling some specific instruction here. In RISC-V supports this through this JALR instruction, yeah, you sort of do the call and then you return where you came from. So this code, it's also we argue it needs trustworthy verification. So for the classic verification task is translation validation, that you have already verified the code, and now you at the source level, and now you actually need to kind of check that your compiler spit out something that makes sense. But you can also maybe analyze something like execution time bounds in real-time systems. So you may not have a cost model at the level of the language. So maybe you need to do that at the level of machine code or binary code. And there are also other things like low-level security properties, like absence of side channels, that you may have to check that may not exist at the source language level. There are certain challenges here. So a lot of things come from kind of what information is missing, right? So you have these things like indirect jumps, where you may have to kind of look at the provenance of the data to figure out where you're heading. You have memory aliasing, and again, not a lot of typing information, and there may be lots of different kinds of code that you want to analyze that are subtly different, like x86 assembly versus RISC-V assembly or something like that. So our contributions in this work, so we propose general symbolic execution theory for basically suitable for theorem prover use, that is adapted for this kind of unstructured code. And we implemented it in the whole for theorem prover. There was already an intermediate language called Beer that we instantiated this theory for. So that was kind of a concrete programming language. And then there was already tooling around this, so we could translate from, for example, RISC-V to this intermediate language. So we implemented these automatic symbolic executors. So these are kind of programs that apply symbolic execution rules and sort of derive some information about the program. These were different for us for different kind of instruction set architectures due to the different properties we were interested in. But we applied it specifically for RISC-V. We looked at proving these horse-style contracts pre and post condition, and the execution time bounds specifically for ARM Cortex M0. So this is a very simple ARM processor that uses the ARM v7 instruction set. So that's what we did. And so just to give you an idea what this theory is about. So there's kind of a concrete side of the picture. So the theory is general, but we will kind of our target all along was beer, right? So we have a set of labels, and we have some concrete states that consist of a program counter, where you are in this set of labels, and then you have a store, which is some kind of partial mapping of variables to values, and the values will typically be things like machine words of some size, right? And then you have some total and deterministic step relation, which you can kind of repeat, and so you can say like I want to do n number of steps, and this is kind of a restriction versus maybe other fancier languages, right? So some assembly sort of fulfills this. Semantics for ISAs sort of can follow this. And then on the symbolic side, we have a symbolic state where the main kind of addition has become this mapping. The store is now a mapping from variables to symbolic expressions, so it's not necessarily, which may include these symbolic variables of some sort. And then we have path conditions that sort of say what does this represent in some sense? What path in the program does this represent? And then we have an interpretation which maps these symbols to concrete values. So if we want to kind of derive something about the real program, then we have to have this kind of interpretation. And just to give a very tiny example here, so you can sort of, the program is so small here that we don't even show the labels because they're not so interesting, but just have some program that conditionally does some kind of increment. So if you have some kind of initial symbolic state, you may have these symbolic variables alpha and beta that are assigned to these variables. And then you do your symbolic execution, and you end up having two different symbolic states, so one for each possible path condition where, for example, b is equal to 0 is not equal to 0, and one where b or beta in this case is equal to 0. And then you end up with a different symbolic store in each of these states. So that's kind of the game we're playing here. So just to sort of give a very quick kind of rundown of the theory here. So we define something called a matching state. So the symbolic state matches a concrete state through an interpretation if they have the same program counter variable or program counter value, and then you can sort of do this interpretation of the symbolic store and get the concrete store, and then the path condition is true, right? So then for if we want to allow sort of a little bit of deviation from on these variables that may not matter, right? So we have also something called a loosely matching state. If there is this interpretation h prime that is a subset of or h, the original h is a subset of this h prime, and then you have this matching state for that. So this finally gives us the definition of what we call soundness or symbolic execution soundness, and also the definition of our main kind of data structure that this whole formalization builds on, which we call a progress structure. So this consists of a label set and this symbolic state, and then a sort of target set of symbolic states, right? And then so you can sort of relate that to these states, and you say that there exists this S prime where you've taken some steps, and then there exists a corresponding symbolic state which loosely matches this original symbolic state. So maybe it's easier to kind of show this in an illustration. So essentially, for all interpretations, this H and this state that takes this that has this matching. So we start with a symbolic state, and it matches this concrete state, and then there exists some S prime that takes a number of steps in our concrete semantics. So again, doing the actual program executing, and then there exists this S prime symbolic state which loosely matches this original S prime. Okay, so that's the general idea here. So then once we sort of set this up, this notion of symbolic soundness, then we can start to define rules how to derive this. And this is kind of the main ingredient in what we call like a symbolic execution engine. That so these rules are kind of possible operations that you can perform in this symbolic execution engine. And then later we will sort of use these rules in various ways to implement these executors that will automatically kind of symbolically execute the program, and then we can use that information to derive various properties. So these are kind of show the flavor of these rules. So you have some kind of the set of all symbolic successor states, and yeah, this is then you can derive obviously that this is a sound progress structure, and then you can have substitution. So this just is about kind of changing a name, very simple operation. And the condition here is just about kind of not getting things bound when they shouldn't be bound and so on. So some more complicated rules like simplify. So this allows us to kind of manipulate the symbolic store in various ways. You can introduce a new variable that maps to some kind of symbolic expression. And we also have a rule consequence that allows us to, for example, simplify these path conditions and so on. So I'll give you an example, just how you sort of can use this. So for example, if we look at this very simple program that we had before, or sort of the result of symbolically executing that. So we have these two symbolic states, right? One where we had a path condition where beta was not 0, and one where it was 0. And then we can say that, oh, we don't actually want these two different symbolic states. We can sort of merge them together by having a single path condition. But then we sort of lose little bit. You can see that we lose some kind of information here when we do this. So we just put the alpha in an interval instead of kind of keeping around the information that beta was 0 or not 0. So these are kind of possible operations that we could do depending on what kind of verification task we are interested in. So essentially we implemented, so there are a bunch of more rules, and you'll have to look at the paper for all of them, but they are trying to capture all of these kind of common ways of making symbolic execution efficient. And we proved them all kind of sound with respect to in this way I just showed you. And then we sort of implemented on top of this in standard ML. So if you know Hall 4, it's basically a theorem prover embedded in the standard ML language. And this means that basically all your proof automation is written as standard ML functions, like building these kind of theorems that are representing the formal proofs. And in this implementation, so the symbolic execution theory is completely standalone, so it could be reused for other purposes, but of course it's very adapted for our use. And again, we use Beer as the concrete language here, so it's a sort of general abstract assembly language. And then there were already implementations of proof or sort of semantics preserving translations from for example, RISC-V and RV8 to Beer. So we kind of piggyback on that to sort of get things to Beer, and then you can symbolically execute at the Beer level, and then you can use the results for various things. Okay. So here is the kind of general architecture here. So maybe one flavor that is different from a lot of, so there are many tools that have this architecture, but our goal here was to kind of defer everything to the ISA model, or everything should be expressed in the end in terms of a separate model of the ISA, which we, in our case, comes from this L3 language, which is, for example, used by ARM, I think, in some respect internally. And in this work, we focused on the RISC-V definition, for example, of the ISA. And then we do this translation. So this was done in earlier work to Beer. And then further here to the symbolic execution part. And of course, you can also reason about beer manually inside the whole 4. So there are various rules for example, using weakest precondition and so on. But the game here we were playing is that we want to kind of give people actual proof automation instead of manually applying these core logic rules and so on. But you can see here that it sort of feeds into an existing contract theory, which also exists both for at the ISA level and also at the beer level. So somebody had already set this up in earlier work, or subset of the authors of the paper. So essentially, the symbolic execution rules are this, as I said, of operations in this abstract machine, and we implemented these executors, and they are also the ones doing this kind of optimizations that are common in to make symbolic execution scale better. So things like the post-processing pruning and so on. So there, of course, there are rules for pruning state, so it doesn't explode. Yeah, we sort of generate these progress structure theorems, which is essentially a way of saying that, you know, when we kind of run these functions, they produce this whole 4 theorem, which contains the kind of actual data structure itself, but also kind of a witness that it has these properties that we want, right? So usually this is called proof producing in whole 4. So we sort of measure, like, could we actually make this efficient? So I think in the beginning it looked quite bad. Actually, it took many minutes just for small programs, but in the end we got it down to quite manageable times for, you can see here for AS, for example. So you take a few hundred instructions, and it can take up to a minute. So typically how it scales is with the number of instructions, but also with kind of how much is stored in the symbolic memory, right? So for example, if you know your ciphers, you know that they basically all the output bits depend on all the input bits. So there's going to be a lot of operations that you kind of need to keep track of in this symbolic store. So that's why you can see that ES and Cha-Cha take quite a lot of time. Yeah, so we looked at applying this specifically for functional correctness of RISC-V binaries. So again, we leveraged this earlier work on binary contracts for RISC-V and for beer. And essentially, we assume that you start with a RISC-V contract, and then this has to be currently manually translated to beer. This could be automated, but probably for a small fragment of contracts, because essentially now we write them in whole 4. You can write anything, right, using the RISC-V state. And then the idea is that you use these preconditions as path conditions in the beer program, and then you try to prove this strongest post condition, and that allows you kind of to get the post condition. So essentially, yeah, we have already from this library that we use, we have the connection between beer and RISC-V maintained by a simulation relation, which we have as a theorem in whole 4. So here's what it looks like in practice, this proposed verification workflow. So essentially, you don't have to have a source code program, so you could just start with a binary. You don't even have to use disassembly. You can kind of just use the binary directly. But at least I found it a lot easier to work with disassembly, because you can sort of at least see a little bit of what's going on instead of looking at a hex editor or something like that. But essentially, after you have the disassembly, you write some specification for it, and then you translate that to this beer language. And then you run this and get this progress structure, which again is both like a data structure and the theorem, right, that it has these desirable properties. And then you prove automatically this beer contract. And of course, this could fail. So this is not a complete workflow. And finally, you do what we call backlifting, which is taking the beer contract and translating it back to a RISC-V contract. So the whole progress structure to a contract, so this is kind of where the theory meets the practical use. So we have a theorem for that. So essentially, this theorem, so I'm not going to go into too many details here, but essentially just reducing, we assume that we have this progress structure thing, and then we reduce it to proving these 3 conditions here. And if you can do that, may not be possible for various reasons, then you automatically have this kind of proof of the post condition, right? Okay, so let me give you one small example here. So the easiest example I could think of, which was RISC-V contract verification. So just adding a single instruction. Here is what the precondition and postcondition would look like. So the only kind of discrepancy here is between like the A0 in the assembly and the X10. So this is just like a different name for the same register in RISC-V, right? So you just say that you increment this register, go on. Finally, you get a kind of RISC-V contract after you have done the symbolic execution. And this says that if you start from executing this program at a label and then you stop at a certain other label, then the post condition will hold. So this is just, so we did some case studies here, so I'm not going to go too much into them, interest of time here. But yeah, the ciphers, we did SHA-SHA-20 cipher, and we also did some kind of handwritten assembly, just things that are outside what you can prove with verified compilers. And yeah, it takes a couple of minutes to prove that. Maybe I'll skip that. So the other application we have is for execution time bounds. So this relies on this very simple processor that essentially has no very short pipeline and no cache. So essentially, this means that we can have a symbolic variable representing the clock cycle counter, right? And essentially, when you have these two paths, you can have different symbolic paths, and then you can merge them, and then you can use this kind of interval idea to maintain sort of what is the maximum this clock variable maximum value that this clock variable can be, and what is also like the least value that this can be. And this becomes the sort of best case time, right? Or worst case time. And yeah, with this analysis kind of reduces to this L3 semantics, which was not done by us, basically. So we compare this to testing on hardware and a tool called AIT. So I won't go through too many of these numbers, just to say that we managed to prove for AES, at least for the loop, you have constant time on Cortex M0. So AIT was actually unsound on this. Even though it says the same number of cycles here, actually they count cycles a little bit differently. So this was a bug that we reported, and it was fixed. And we also compare this to just testing on real hardware. So this was another thing. But you can see here that the time it takes can vary between 10 minutes to up to an hour for bigger programs. So this is kind of what we're playing with here. And yeah, so just to compare it to other binary analysis frameworks. So again, most of them are not sort of grounded in a theorem prover, but some other works also use. I mean, they usually don't do what we do, which is basically deeply embedding the symbolic execution. So they may use symbolic execution, but they sort of have that outside of the theorem prover itself, which is another kind of set of trade-offs. So we use, and just to point out that we also use a little bit of SMT solver C3 for discharging some conditions here. So we think we got the trusted computing base down a bit, but it can probably shrink even more in the future. And yeah, so that's kind of it. So we have this general theory, and again with these assumptions about labels and deterministic execution and so on, which probably does not hold for a lot of general languages. And we implemented this in Hol 4, and we instantiated this for this beer language. And so essentially all these theorems and definitions I showed you, they are all kind of available in Hol 4. And you can check on GitHub if you want to see what we did. And essentially, yeah, every verification tasks become just a few like theorem prover files, and that's how it works. And that's it.
Thank you, Carl. Any questions in the audience?
Okay, thank you for the talk. Very cool, I would say. I would like to know, you are basically doing over approximation of the results. If you have the, for example, the timings, you are over approximating the execution time, basically doing an interval between the best case and worst case execution time.
Oh, yeah.
What if the interval is too coarse? Do you have some way to refine this? If basically you compute too bad worst case execution time?
Yeah, I mean, so essentially this is like, we have a kind of toolbox, right? So we could implement all these kind of things like coarsening the intervals and so on. So I think Andreas was the one who worked mostly on this execution time stuff. So I think he found some kind of reasonable trade-off specifically for Cortex M0. But he could probably like play around with it and, you know, if he needed some better approximation or stuff like that, right? So that was one of the points of the work, that this was supposed to be very flexible. We don't commit to a certain strategy. And this was just like one possible approach to doing this execution time stuff.
Okay, thank you.
Any other question? So I have one. So you presented us the different rules that are sound in your system.
Sure.
But then how do you pick and choose the right rules at the right moment so that your analysis is actually effective?
Yeah, so this is, I guess, trial and error was. So again, my colleague Andreas, he worked on this for I think many months to figure out like, you know, what is the best combination of rules to actually make it scale. And I think we had a lot of problems with the symbolic memory just exploding, right? So then you had to implement various ways of pruning and so on. So I think we didn't have, like, there was no, it was mostly a process of trial and error, trying it on actual real programs and sort of seeing where it failed, right?
So you have not found any methodology like for dealing with loops or?
So loops are actually kind of, we consider them a little bit outside of the scope of our work, right? So you can sort of, what we do instead is that we can kind of slice the program and analyze, for example, the loop body and the you know, the loop condition and so on, right, separately. And then this is like the translation validation game, right? So somebody else can do the, you know, the fixed point proof or whatever. So.
Any other question? No? Then let's thank Carl. And this was the last talk of the session.
Okay, good afternoon, everybody. So we will start by a keynote talk given by Anthony Dean. So he is an expert in automata and logic from MPI and then University of Kazakhstan. And then today he will talk about like transformers, the one from Gen AI, and then to understand it from the angle of automata and logic. Thanks, Anthony.
So thank you again for the introduction, and thank you again, Yifang, Thomas, and Ondra, for inviting me to give a talk. So this is, by the way, a topic that I don't usually talk about. So I've started working on the topic pretty much the last 3 years ago. I guess so. When I was invited to give a talk, I thought like, okay, I should give a talk about something that is a little bit different that you don't normally listen to at VMCAI. So this is why I came up with this topic. So, but hopefully I can convince you that logic and automata and verification have its place when you want to understand transformers and when you want to, analyze and get better understanding of transformers. So maybe just a very quick question. So how many of you know a bit about, okay, so I guess everybody has used LLMs before, obviously, right? This is not to us, I guess. But how many of you know a bit more about the architecture of the LLMs, let's say transformers? Can you raise your hands? Okay, yeah. All right, okay. So I will go through it a little bit more slowly, because the notation is also a little bit different anyway. So, but anyway, so without needless to say, so transformers is so transformers are a model that was proposed around 2017, around this time. The purpose was to overcome the limitation of RNN. And this was took a picture or screenshot of this like around a few months ago. I'm sure it's now become like, 200 something thousand, so the number of citations here. But this is the basic model behind today's popular LLMs, some of you might have tried some of this one. So maybe GPT or Gemini or others. Okay, but transformers, if you think about the model itself, so transformers as a model, these are an inherently sequential model. That is, so what does it mean by sequential model? So what it means is that the input is a text, it's a sequence, it's a text, sequence of tokens. Typically, you don't really have a bound on the size of on the length of the sequence. So unlike classic feed-forward neural networks, so you get a sequence or a text like this, and when you run transformer on a text, the output is also a text, Could be, for example, something like this, Okay. So what I mean by transformers in general, I don't really mean a specific large language model, foundational model. I actually just mean like the architecture of transformers itself. So it could be a much smaller one, Okay, so of course we know that transformers can do a lot of amazing things, but interestingly, transformers are also known to be bad at certain things. So, so this is, for example, a task that is known to be quite difficult for transformers, that is doing counting and doing arithmetic. So this is an example that no longer works, I actually tried it about few months ago. It worked, and then now it doesn't work anymore. But anyway, let me just show you. So for example, it's pretty small. I'm gonna try to read it for you. So for example, you can ask GPT to count the number of A's and B's. This is like a really trivial example, but just to give you a simple example, it's not so obvious. So I'm gonna give a string A's and B's, of A's and B's, and then you ask GPT to tell whether or not there's an even number of A's or even number of B's. So this is a very basic, simple kind of counting, So in particular, you just need to know, you just need like one bit to know, right? Like to remember whether or not this is the parity of the number of A's. Okay, so after some after some conversation, you can, for example, input some string like this, and then what it says here is that, okay, so for example, this is the output is like this, let's say 19, it has an odd number of A's. Yeah, but unfortunately, if you run this, yeah, like using Python, for example, actually the number of A's is actually not really 19, it's actually 22. Okay, so this is one such example here, yeah, so that epitomizes the problem with counting. And this anomaly was actually found already some time ago, yeah, in particular by these groups of authors. So in particular, there was they consistently showed that there's a problem when you want to train a transformer to recognize the regular language parity. That is basically, when I say recognize, I'm talking about to classify the strings that belong to this language. So it's a very simple classification task, yeah. Okay. So of course, when you see this kind of phenomenon in an experiment, what you want to do is you want to try to understand, like, is this actually even expressible by a transformer? Is this, if yes, is it really trainable? Right? And this is, in fact, one of the main questions that has driven the field of connecting formal languages and neural networks. Yeah, and in particular, there's quite a lot of people that have already started working on it. So it has a highly active Discord channel with 500 plus members. Yeah, and rapidly growing number of publications as well at top ML venues. So let me just show you super quickly here. It's a bit small, but actually the main results in the field were from, like 6 years ago, 5-6 years ago. In particular, this result that actually shows that parity is quite difficult for transformers, but on the other hand, you see something that looks a little bit contradictory. So parity is difficult, but then how come transformers are Turing complete, right? So you see that when you get into the field, you always get this kind of feeling that how come everything looks contradictory? So we will talk more about that, yeah, during the course of the talk. And one thing that I can say is that there's quite a lot of different models that people look at. Yeah, so in particular, so this one here, like a lot of people used to, and actually still think about transformers when it's kind of like doing shallow thinking. So this basically when you this is like as an analogy, maybe if you run GPT, you want to get an answer quickly, right? You don't want to wait for too long. So if you're happy to wait for a long time, yeah, then maybe you can solve more. Yeah, so this is basically this thing about chain of thoughts. Okay, in particular, so these are the results that have been around, and you can also ask, what can transformers do in general? Like, if we already, if you want to use regular languages as a guide, as we are verification people, can we classify any regular language? Can we solve any computable functions? And also from the point of view of programming languages, yeah, can we provide a clean declarative language that characterizes the expressivity of transformers? Yeah, and so these are like really fundamental questions. If you want to do any analysis or verification, you first need to be able to have some kind of semantics, right? So, so once you have this, which is actually not even solved here, not fully, you also want to ask, can we automatically verify transformers? Like, is this even decidable? Can we exploit verification techniques like IC3 and stuff like that? And if you want to like relate it to something that also appear in practice, yeah, there are so many kinds of LLM attacks out there. Yeah, can we also use this to verify LLM attacks? Yeah, against LLM attacks. I mean, this is a bit far away, yeah, but I just want to show you that this is probably what we want to reach, but this is not really. We are nowhere close to that. Okay. Just checking the time. Yeah, so this is the outline of the talk. So I'm gonna mainly focus on the kind of formal models of transformers. Yeah, I'm gonna take you guys through the examples. Yeah, and I will mention some what can be done for verification, throughout the talk. And also, I will make a remark. So most of the stuff that I'll talk about is they basically concern models with no chain of thoughts. Yeah, basically the ones where that are mostly used, yeah, in practice. But if you want to use chain of thoughts, yeah, this can be done. So we will talk as well about that. But I will make only a remark about that a little bit later. Okay. So as I mentioned, so we'll talk mostly about transformers as binary classifier, yeah, of strings. That is, it's a language recognizers. Yeah. Of course, transformers can do more stuff, yeah. But at least if you want to understand anything, as we know already from like computability theory, we want to be able to look at something as much simpler object first. Okay. So by the way, if you have any question at any time, just feel free to stop me. Okay. So I'm gonna. Okay, so before we go through some of the models, some of the main models of transformers, yeah, I want to first just make a general remark first. So one of the things that you'll find out about the field is that there are really many possible variants of the models that people have proposed. The reason behind it is there's really a lot of parameters that one can really look at, yeah, and all of these things give rise to different models with different, often with different expressivity. So, for example, one of the things is something about precision. How much precision do we allow, yeah, and what kind of attention mechanism do we allow? Are we allowing uniform or non-uniform models? And also, last but not least, you also want to ask how much do you allow, what kind of positional encoding do you allow? Yeah. So this is only like some of the questions, but there are actually even more parameters out there. Yeah. So I guess what I want to say is that if you see there's a lot of different models, you know, like with a table of so many things. Yeah. So please don't feel discouraged. Okay. So let's try to take a simplistic view of transformers first. So what is a transformer? Right? So a transformer as a language recognizer, so I'm going to have like some inputs like this, A, B, text, yeah, a string, A, B, A. So as I mentioned, so you given this, what you're going to do is you want to just, in our case here, because it's a binary classifier, you just want to output 0 or 1, right? But transformers are actually, you know, models that extend deep neural networks, yeah, like feed-forward neural networks. That is, they actually don't work on text, but they work instead on vectors, yeah. So what you need to do first is you need to first convert them to vectors. So for example, this is the simplest one, hot encoding. You can embed A as 1, 0, B as 0, 1, and so on and so forth. So now you get a sequence of vectors. And what I'm going to do is that I'm going to run this through a transformer, and I'm going to get also another sequence of vectors as an output. And at the end, I want to decide whether or not it's accepted or rejected just by, you can do it differently. But one way of doing it, for example, you can just take a linear combination of the last vector and just check if this is like less than 0. So this is just a random way of doing it. You can do it equals 0, bigger than 0. There are many different ways of doing it. Okay. Now, there's also another thing that people usually use. As I mentioned here, there's something called positional encoding. So positional encoding is, so when you embed this A, B, A, yeah, sometimes you also embed the position, some kind of positional information to the vector. For example, this is at position 1. I can put 1 here, and then I can put 2 here, 3, 4, and so on and so forth. Yeah. So this kind of positional encodings that people use, in practice actually can be quite complicated. Some people use sinus, cosine, and so on and so forth. So yeah. But so this is there are different kinds of PEs that you can use. Now, okay. So that's a transformer, but actually this box here is actually not just a single box. Yes, it consists of a number of layers. So what you do is that you run through all of these layers one by one until you get to the end, just like a normal feed-forward neural networks, deep neural networks, for example. Okay. So I'm gonna concentrate on just to define a little bit, yeah, on how it works. just for those of you who've never seen it. So transformers, this is a case of transformers using one of, let's say, just only with one layer, yeah. So when you have more layer, then yeah, just simply compose them as functions. Okay. Right. So each layer is equipped with several information. So usually you have some affine transformations, just linear transformations plus a constant, yeah. And then you have this piecewise linear function. So this piecewise linear function is actually simply just a composition of linear transformations plus a ReLU, yeah. So ReLU basically you just check whether or not it's 0 or it's maximum of 0 and a number, yeah. Okay. So this we call this piecewise linear. I mean, I don't know why, but that's what they call it. Okay. So all right. So once you have this, so you have this information. So this can be encoded finitely. So the question is, how do you compute this W1 up to Wn's, right? So and then in order to compute this, the first thing that you need to do is to compute the so-called attention matrix, yeah. So because as you can see here, this is V1 up to Vn. So what you need to do is you need to be able to somehow so for you need to come up with W1 and up to Wn, right? So for each of the V1, the best thing to think about it is to simply look at so each position can communicate with any other position, yeah. So this is basically why you want to come up with some kind of matrix here that kind of determine how much communication you need to have, yeah, with between each other. Okay, so so this is done by this matrix, yeah, this attention matrix, and this attention matrix, each of the cell here is the so-called attention score, yeah. So for example, here at this position is going to have the attention score between V2 and Vn. So the intuition behind it is like how much attention. So let's say this is the anchor, V2. How much attention should I give to Vn? Okay, how much attention I should give to Vn here, and this is given as a dot product typically, yeah, between this V2 and Vn, like initially preprocessed with A and B's. Okay, so the detail is not so important really, but what you get is a matrix that is of this form, right? Okay. Once you get a matrix, well, it's n by n, and now you need to collapse it into a number, like into n numbers, right? How do you do that? Well, in order to do that, the most common way that people have done so far is to use also what people do in practice is to use softmax attention. Yeah. So basically, what you do here is that so you need to compute a number. So for example, like let's look at V2 here. So you need to compute out of V2, you need to compute this W2. So in order to do this, the first thing that you do is I'm going to look at this row. Yeah, I see 8, 8, blah, blah, 1. Yeah. So out of this row, I'm going to convert it into a probability distribution. So this is the intuition behind this. Yeah. So probability distribution such that for each of the position, it's going to be simply just the weight that corresponds to this 8. Yeah. So it corresponds pretty much to 8, but this is it's now become a probability distribution. Okay, so the sum of this thing should be 1, right? Okay, and what I'm gonna get now is a weighted sum, yeah, of the VJs of all of the places, yeah. But the weight here is given by the probability of each V, yeah. Okay, so that's typically what people do. So intuitively, again, you know, the intuition behind it is, so I'm V2, right? I'm gonna look at around me, yeah, and I'm gonna have the how much I need to pay attention to anybody, but I want to pay attention to everybody, right? So I'm gonna pay attention to everybody, and I'll kind of like get a glimpse of what people have. Yeah. So this is essentially what you do here, like when you do this kind of a sum. Okay. Right. So this is a little bit tricky to analyze. As you can see, there are several problems. The first one is that you have a problem with the exponential function, and you also have a problem that nobody can really get a 0, actually. This is also the other problem here. So you don't really get a 0, so it cannot be a 0. So you have to take into account pretty much everybody. And when you do analysis, it has turned out to be quite difficult to analyze. Okay. So one solution that people have looked at is to look at an approximation of softmax extension. One of them is, so this is typically called hard attention. So what you do is that, so for those values that are not really that big, yeah, so okay, so I'm only going to look at the values that are the biggest ones. So basically, yeah, so I'm only going to look at the attention scores or the positions that have the biggest or the maximum attention scores. For example, if you look at this row again, yeah, so I'm going to have, for example, this is the biggest one. This has the, so for VI, V2 has the biggest attention score, so I'm going to only focus my attention on this guy. And in the case of V2 here, so I have only 2 places, so I will pay attention to these 2 guys, yeah? So both of them have maximum scores, and so on and so forth, okay? So the important thing is like the guys that don't have, yeah, the guys that are not really the biggest, yeah, we just ignore them, okay? This is also what people do in practice, right? We only look at the big guys. All right. Okay. So once you have the UIs, yeah, that you have computed before, what you do then will just be to do another post-processing. Yeah. So you find the value. So I'm gonna just apply a piecewise linear function like ReLU and blah blah, and then to get this WI, right? So that's essentially what you do here. All right. Right, so that's the model, and just as a summary here, we have so basically what we've seen is we have hard attention and soft attention, yeah. And if you look at hard attention, they are actually I kind of didn't mention this, yeah, but it can be mentioned super quickly. So there are different ways of picking. So if you have 2 guys that are of equal with equal attention scores. So there are different ways of breaking ties, yeah. So the first way to break tie is to just pick the rightmost vector with maximum score, yeah. So or leftmost if you like. Another way of doing it is to for example just average them, okay. So this one, all of this thing gives rise to different model with different expressive power. Yeah, as I mentioned here, softmax attention transformers, so it's more complex. So people instead usually use some kind of average hard attention transformers in order to approximate that. Okay, all right. So we'll talk about we'll talk mostly about these 2 models. I will mention this every now and then. Okay, so just to go through 2 more things, yeah, and then I think we should be done with the model. Another feature that people usually use is the so-called positional masking, and what it is simply this is used a lot when you do in practice, because like typically when you look at transformers, it's an autoregressive model. So usually you look at an input, you take an input, and then you output something, and then you run it again, and then you output something. So it's basically what you can look at any given point in any position is always, you can only look at the pass, yeah. So this is what they call strict feature masking. That is, attention scores, you can only look at attention scores of earlier positions. Okay, so let me just tell you here how it manifests. So before here, this is n, right? So it means that you can look at everybody. You can look at when you're at a different row. Sorry, let me just show you here. Okay, at any given row, you can look at everybody, right? Before, but now. So with strict feature masking, you can only look at the rows, the positions that are smaller than you. So if you are V2, I can only look at V1. If you are V7, I can only look at V6, V5 up to V1. Yeah. So this manifests in the this kind of formula here. So where you simply have the sum here, like it's supposed to n here, you get like I minus 1 here. Yeah. And also for the high attention, you only look at the VJs here that that come before VI. Okay. So for example, the effect here would be like, before it was here 7, but now here, like, it's actually only here. Okay. So as I mentioned, the most recent models employ strict feature positional masking. Okay, I think that's pretty much the model. So can I ask if everybody is kind of on board? Yeah, good. Okay, so what I'm gonna do is the following. I'm gonna go through the two models, like U hat and A hat, one by one, and I will tell you what kind of results that people have come up with, and in relation to expressivity and also to verification. Mostly focusing on this, yeah. All right, so the first one, this is a very useful connection, yeah, but I will not talk about it too much. It's the connection to complexity theory. So I'm only a user of complexity theory, and this is like a really good application of it, for example. This was proven, like a few years ago, that U-hat, the class of languages that are recognized by this U-hat are in the circuit complexity class called AC0. I don't know how many of you have heard of it, AC0? Okay, yeah, so the intuition behind it is, okay, so firstly, let me just say what it is. So these are basically problems that can be solved by families of circuits with constant depth, yeah, so the depth cannot increase, yeah, it's only like constant, and the size of the Boolean circuits only grow polynomially in the size of the inputs. Okay, and then there's some minor details that I didn't mention that you need also unbounded fan-ins. Yeah, so for example, if you have an AND, this has to be you need to be able to have ANDs with multiple inputs. So these are actually languages that are like can be very efficiently parallelized. But the catch behind it is that it's also pretty weak. So for example, you also know that you cannot do parity. Parity is not in U-hat, yeah. So this is a deep result. I mean, of course, like complexity theory is full of results that, that are okay, so full of conditional results. We don't have anything unconditional, but this is unconditional, okay? There's no like NP complete or anything, okay? So this is like, this is known to be the case. This was proven many, many years ago. Yeah, quite complex proof. Okay, so let me just say super quickly here. So this gives you, how does it relate to the question that we asked earlier, right? So this like this anomaly, like the that transformers cannot do parity. So this could give you a candidate for a model of transformer that, like faithful to real world transformers, and at the same time maybe more analyzable. So this is kind of the background behind it. So okay. So that's at least that gives you some kind of an upper bound, yeah. So what kind of things you can what kind of things you can recognize, but what can you actually do? So that tells you what you cannot do, but what can you do? So we have some results here, yeah, from these two papers. So let me just give you a summary first, and then I will go through it in more detail, yeah. So remember, one of the motivations for coming up with, for studying this, is we want to be able to have a better clean declarative language that allows you to express transformers, like if you want to write it down by hand, let's say, right? So that's what we want to do. So this is, this should be interpreted in this spirit, yeah? So we want to have a characterization of this transformers, or class of transformers, using some kind of a logic. And this logic turns out to be a logical fragment of AC0, okay? And when I say characterization, of course, the best thing would be like to have some kind of equality, if possible, yeah? And it turns out some kind of equality can be shown, yeah? And it's highly connected to the so-called star-free regular languages, or if you know LTL or first-order logic, so it's all the same thing. Yeah, and this actually also tells you when you look at the proof, it actually is it's an effective translation. So we know that if you only just want to, if you're just interested in U-hat on its own, yeah, that has fixed precision and only strict feature masking, we know that this is verifying this. So I mean, like emptiness and so on and so forth is decidable. Okay. So what is this language? Well, I mentioned star-free regular expressions. Yeah, so I'm sure some of you, or maybe most of you, have heard of it. But in terms of verification, and also to be closer to the model, we can look at the this LTLF, pure pass LTL, finite LTL, finite trace LTL instead, which Moshe Vardi has looked at a lot in the past 10 years or so. Okay, so the model is very simple. You just basically it's just normal LTL, yeah. But what you do is that you have, instead of looking to the front, you actually you only look backwards, yeah. So I can have I can, instead of next, I have like the inverse of next, which some people call yesterday, yeah. And instead of until, I have like since, yeah, right. So the meaning of this thing is really what you expect, yeah. But yes, maybe some kind of quirkiness just for the purpose of translation. Sometimes we make it strict, yeah, but this is just for technicality, yeah. Okay, so this is just basically the previous guy, and phi as psi is basically just walk backwards. Walk backwards, and everybody has to be phi, and at the end you have a psi, right? But so we use the strict semantics here just because it's easier for the proof, yeah. Now, if you have LTL, of course, you interpret it at the beginning, yeah. But if you have LTLF pass, pure pass, yeah, then you interpret it at the end of the string instead of the beginning. So you really just have the same thing, yeah. Okay. So I will give you like a bit of a flavor of how the translation goes, yeah. Like nothing really deep, yeah, but just to give you a flavor. But one thing that can be just before that, I just want to mention super quickly, if you look at the translation on its the translation itself, yeah, and want to be able to do verification, then of course complexity matters, yeah. And it turns out you can do pure pass LTL-F, yeah, to U-hat in polynomial time, yeah. So this is so it's U-hat is at least as succinct as LTL, yeah. But it turns out it's actually also exponentially more succinct, yeah. So in the sense that you can be also, if you want to verify U-hat, it turns out it's actually 1 exponential higher, which also incidentally could be a potential domain for automatic verification. Nobody has really looked at it, yeah. But just to mention that, I think it could be maybe an application of IC3 or something like that. Okay, so I don't think there's a lot of time, but I will just maybe, in the interest of giving you a bit of a flavor, I will just go through this super quickly. So let's take a look at this very simple formula, yeah. Okay, this very simple LTL formula. This corresponds to this regular language. Okay, and let's say the input is A, B, B, A, A. Okay, so as I mentioned, so the strings have to be first converted to sequence. So I'm gonna use the encoding that I had before, the one-hot encoding, yeah. So this A, B, B, A, A is gonna become this this sequence of vectors. I'm not gonna use any positional encoding here. So this is basically just gonna be the input like that. Okay, so the key idea behind the construction of U-hat is you first want to label each position I, indicating whether or not the formula psi is true at for any psi, for any subformula psi of the input formula here. So I'm gonna label it with information that indicates whether or not psi is true at that position. Okay, so this is just like a standard. If you know the standard LTL to automata construction, it's a little bit like that, right? Okay. So after first layer, so if I just like label it, I'm gonna, so I will tell you how to label it, but I'm just gonna tell you how the proof goes. So first I'm gonna like label 0, 0, 1, 1, 1. So basically this because, for example, here 1, this is, I'm gonna look at the I'm gonna look at this ASB, yeah, as the first subformula, and the second one is the entire thing. Okay, and then if you look at the first one here, this is true, 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 like this one here. Okay. And then after for the second layer, I will do the same thing, but I will just keep extending. So the output of the second layer is just going to be the same thing, but I'm just going to extend it by one more information that indicates whether or not the entire formula is true at that position. So if you have this information, what can you do to read out whether or not W is true? You simply have to look at the very last position, and just the very last position of the very last vector. Okay. Okay. So maybe just let's go through just one example, idea for layer 1. Layer 2 is pretty easy. Okay. So the idea here is, so this actually has several sublayers. But if you have something like phi as psi, what you want to do here is you want to find the first position. Yeah, you want to find the first position such that not phi or psi is true. Yeah. So this is because the semantics, you need to find somebody such that psi is true. Yeah. And then before that, phi has to be true, right? So I'm gonna label each position with not phi or psi. Okay. And this actually requires two sublayers, just some details. Yeah. This actually turns out to be just B, yeah, so we don't actually need to do anything because we already have the information of B. Okay. And once you find this position, yeah, what you want to know is whether or not psi is true, right? Because at this position psi has to be true when not phi is when not phi is false. So you need to know that psi is true at that point, right? Okay. And in order to do this, yeah. So first you find that position, and then what you need to do is just need to the information here, yeah. So whether or not, so if you can find it, yeah, then this formula is true. That is this formula is true. Sorry, if only if it's found, yeah. This such a position is found. If only if what you forward here, yeah, the value here is 1. Okay, so you want to know that psi is true, right? Okay, so what you do here is that just to fill in a bit of details. So what you do here is just the attention score here at position J here should have this value, as I mentioned, yeah, and here so you find the rightmost position Vj. So if it does not exist, actually it's okay, yeah, because it'll just be 0, and you'll just find this degenerate case. You'll just find the next guy, and the value is 0, so it's okay again. Then once you found this value, if you have this value, then you simply just have to map the n here. Like you need to map this vector here into just vi here extended with the value of this. Okay, and again, this is a bit of hand waving, I understand, but what's going on here is that this value here, you can simply, if you have a vector, you can simply just use an affine transform to just project it to one of the values. Okay. All right. So that's just an example of how things work, and the same can be done as well when you have an x. Yeah. So I'm gonna skip that. Yeah. Okay. Right. Okay. So any question? Sorry, I didn't. Yeah. Yeah, so in this particular case, actually, I don't need anything more than just bits in this particular case, yeah, because this is a very basic LTL. So again, the full general result, actually, you can do more than LTL, yeah, but I just want to connect it to LTL because it's you can actually verify it. Yeah. Yeah. So this is we're gonna talk about that in when we deal with AHAT. Yeah. Okay. You have more questions? Or?
Okay, thank you.
Yeah. Okay. So yeah. So so it turns out that you actually have a full characterization if you sufficiently restrict the transformers, especially if you talk only about positional encoding with fixed precision. Yeah, so fixed precision, I think you can think of it like, let's say you have floating points, let's say, yeah, and you still have masking as well, like before, yeah. So this can also be converted into LTL, yeah. Okay, so this it actually is an equality in this case. So this is let's not go through the detail, but I think the key ideas here is that it turns out if you look at UHAT, if you think about it, you cannot actually generate really new vectors. You know, like all the values that you have already computed already exists in the input somewhere, right? Because you only pick a winner, and then you just have to do an affine transform. So it's basically you can symbolically write it down in terms of the input values. So you cannot really generate like infinite number of values here. Okay, so this is important because like if you have that kind of result, this also explains that you can actually also compute an automaton, in fact a transducer, yeah, and each layer can be converted into ladder-to-ladder transducer over using a fixed alphabet, yeah, and their compositions also a transducer, and if you analyze it more closely, it turns out to be a counter-free minimal DFA, which is basically just LTL, yeah, okay, right, okay. So that's essentially like how it's not really, there's nothing really deep here, yeah. Yeah, but what actually turns out to be, as I mentioned, if you look at this analysis here, it turns out that you do need to, in the worst case, generate an LTL that is exponentially large. Okay, so I think that's all I want to. Okay, no, just to recap this again. So I think an open question is, can you verify UHAT efficiently in practice? Let's say with property-directed reachability. Okay, so time, right? So I want to just connect it back to what people have looked at in practice. So UHAT seems to be like a pretty nice kind of model. Yeah, so it's a good approximation, in fact, for transformers under bounded precision regime. That is, for example, using floats. There's some consistency with experiments. For example, parity not expressible, so it's also predicted by the theory. But the problem here is that if you look at stuff like, so there are some problems. So the first one is that there's this language called majority. Yeah. Majority simply like, you have A's and B's, yeah, a string of A's and B's, and this in the language if the number of A's is bigger than the number of B's. So this is not a regular language, yeah, okay? So this seems learnable, yeah? And there's another one. This is kind of the opposite side. There's something called flip-flop language. There's sigma star B E star, yeah? This is expressible by UHAT, but actually it seems to be non-trainable. At least people have difficulty training it. So there's a way to reconcile this, yeah. So there's a way to resolve the inconsistencies. Number one, which is not very nice, I would say. So transformers can actually express majority only for small inputs. So small inputs could be actually whatever it is you care about, yeah. We don't know. The theory actually is like asymptotic, right? So but it could be anything that you care about. So for something large, so it does not recognize majority anymore. So it could be, this is one possible explanation. I think this is true, but then it kind of renders the theory not so super useless, not so super useful. Yeah. So what, in order to reconcile, like in order to resolve the second problem, what people have is they actually came up with a subset of UHAT, yeah, and they have shown that the characterization actually is LTL pass. Yeah. So it's basically, it just means that you only have the pass, yeah, but you don't have S, you don't have X, yeah. So you only have like the pass. It's a bit like it's equivalent to future, but you move backwards, right? Okay. So in this case, if you look at this, then the flip-flop language is not in LTL pass. So this is maybe a better model from that perspective. Okay, so I think that's all I want to talk about for UHAT. I will just talk about AHAT here. I know that I don't have that much time, but I will just, in the interest of showing you something a little bit more, I think it's actually more interesting maybe, I will just at least show a couple of slides. Okay, so let me just begin again with the connection to circuit complexity, not really long, yeah. So before it was in AC0, but now we know that this is an ATC0. Basically, these are the class of languages recognized by, AC0 circuits, but you also have the majority gates as well. Okay, it's known that you can do like arithmetic, multiplications and stuff like that here. So it's still also efficiently parallelizable. Yeah. In fact, if you have circuits up to log depth, they're still efficiently parallelizable. So it's quite consistent with what people see in practice as well. But the problem now is that this doesn't actually help us anymore to show any unconditional inexpressibility. So yeah. But what we can say here is, what about what can we express? Yeah. And this is, I think, a more interesting question. And here we want to approach the problem from a similar kind of perspective. That is, we take some kind of a logical language, and then we want to see what can you express using this. Now, before moving forward, I just want to maybe make a remark quickly. So we know that in AHAT, we can actually do some kind of majority in all these things. Yeah. So that's quite nice. So, and a logic that can sort of allow you to do this is actually this so-called counting LTL. Yeah. So I mean, I make it like they have a name for it. It's called CRASP. Yeah. But this is simply like counting LTL. So we have like LTLF pass, yeah, which is what I wrote before. Yeah. That was a subset of UHAT. Yeah. But now you add counting on top of it. So let's take a look at it. What can you really do here? Okay, so if you look at the logic, the special part is actually only this one, yeah, this sharp phi. So otherwise, it's pretty much, it's pretty straightforward, yeah, just like LTL. So what is this here, sharp phi? So this actually only counts the number of, so at position I, you only count the number of positions that are to your left, yeah, that satisfy phi. Okay, so this basically just you only do some kind of counting, yeah, where the number of times phi holds. Okay. What you can show here is that this is quite interesting because it's actually strictly subsumes LTLF pass, yeah, that we've already seen before. So it strictly subsumes that. So the reason behind it is that you can actually express this pass, yeah, that is f minus 1. F inverse phi, you can simply just write it down like this, no? Sharp phi bigger than 0, no? So phi has to hold at least once next of to the left of me, right? So you can write it down. But of course you can do more, not just regular languages. You can also do like one-dict language, for example. You can do majority, you can do one-dict language. So here this looks a bit like maybe you think it's like a typo, but it's not. So what it says here is that at any given position, the number of open brackets have to be at least as big as the number of closed brackets. Yeah. So that's basically what it is, right? So this is that's okay, and this can be expressed in CRASP. Do you mind if I have 5 more minutes? Is that okay?
Okay.
Yeah, because like yes.
Because we will have 5 minutes for break.
So you have 6 minutes for. I see. So hang on. I thought it's 1 hour, right?
1 hour. Yeah. I mean, okay. I saw that you want to have 1 hour and 5 minutes.
No. I didn't. No. Okay. Okay. Let me just show you here. So we have similar kind of result to UHAT here, yeah. one can show that counting LTL F pass can be expressed in A hat as opposed to U hat here. But there's some extra things here, like so we have to use positional encodings here and also with strict feature masking. So this is a similar kind of result. So you have to somehow deal with the you have to use A hat here instead. If, for example, if you're interested in softmax, yeah, so you cannot really just do. At least it's not known how to do it in softmax, yeah. So you can use uniform layers, but you need something. You either need some kind of like maximum somewhere, or you need some kind of layer norm. So that's so this is an open question here. If you wanna, is it possible to express CRASP in softmax? It's an open question. I don't think I want to. All right, maybe just super quickly. I just say it quickly here. In A hat, what you can do is that you can count the number of times, right? So you can look at so if you so you're interested in like sharp phi, right? So you want to get the value of sharp phi, but what you can do in A hat is actually not sharp phi, but what you can do is a sharp phi divided by 1 or minus 1. Yeah, but you look at frequencies supposed to doing counting. Yeah, so you can do that here in A hat. Yeah, because what you do in A hat is simply you look at the number of times something is true, but then there's divided by the because you do average, right, instead of counting. No? So this is actually a problem, because when you actually want to express CRASP, you don't want these things because every position has a different value. So this is the crux of the entire problem with all of the translation, and I can tell you that, yeah. And everybody solves it using something different, yeah. And it's not known how to do it, cleanly, yeah. So what we do here is that in our case, we get rid of these things using positional encodings. In particular, we use the help of this I and I square in the positional encoding. In order to help you, you need to pick some kind of value j that actually annihilates, so to speak, yeah, this thing. Yeah, so that's the way we do it, but other people do it differently. Okay. Now, okay, so this is just a bit of detail, like technique-wise, right? But why do you care about CRASP anyway, right? So this is what we should ask. Why do we care about this? Now, I think the answer to that is provided by this paper, and I really like this paper a lot, yeah, because it shows you this has a lot of experiments that takes CRASP languages and shows that whatever you pick so far, at least, yeah, it seems to be learnable by real-world transformers. Yeah. So using pretty controlled setting. So this is pretty nice set of experiments. So the authors also conjectured that CRASP captures languages that are efficiently learnable by real-world transformers. So this is a formal version of the so-called RASP conjecture. Actually, this is not true. Yeah. So we disproved this recently, but I think this is still a very nice language. Yeah. So what I mean by we disproved it recently, in the sense that there are actually more things that can be learned. Yeah. So as opposed to there are less things. I think I maybe just want to mention super quickly. So CRASP, the problem is that you have linear counting, but you can also do polynomial, right? So for example, like, you can do something similar like majority, but you have like here to the power of k. Yeah. So it turns out you can actually do also polynomial counting. And we proved this here, that experimentally and also in theory, that not only can you do polynomial counting, we also proved that you can actually also do you can also show that they can actually recognize such languages. Yeah. But the important thing here is that this is the if you assume it's permutation invariant languages, then you can do like polynomials. Like semi-algebraic just simply means any system of polynomials. Yeah. Okay. So this is actually, we showed that this is also bigger than CRASP. Yeah. So an open question is, of course, that is asked by quite a number of people. Can you actually combine CRASP and polynomial counting to get another logic? And is it actually also in, let's say, A hat or softmax transformers? And nobody knows. Now, that's actually a problem, because if you can show that, then you also get this problem, this corollary by default, yeah, that a hat, even like without any positional encoding, is actually also undecidable, because you can just simply reduce from solvability of the Diophantine equations. So that is a problem. But you can ask then, okay, so maybe I don't want these polynomials, and I just look at CRASP. What if I just only look at CRASP instead? Yeah, so I can only do semilinear counting. So maybe I can now be decidable again. Now that's actually a problem, because we also show that this is also undecidable. So because we can also embed the Diophantine equations to CRASP in a satisfiability preserving manner. Okay. All right. Okay. So, I mean, okay, from a theoretical standpoint, maybe not so cool, yeah. But I think it's actually cool, because I'm a verification person, and I'm not afraid of undecidability, yeah. So, and I think the next question is, okay, so can we actually employ some verification techniques for CRASP? And I think this is a really cool problem, because I mean, we only started looking at it, yeah. But the question is very much related to some problems that you look at when you look at this language like Lustre, yeah, which is related to synchronous data flow programs, and which can be reduced to like something like Z3 or CVC5 and so on, right? So we are exploring this this direction, and it seems to be like there's some interesting result that you can get as well here. Okay, so I'm gonna skip the entire chain of thought stuff, yeah. All right. And I'm just gonna mention the future research directions. So we've mentioned like different models here, yeah. So I think there's still a lot of questions about expressibility, like coming up with a better logic. And I think I've mentioned repeatedly the challenges in verification as well. It's not clear. And another thing that I didn't mention here is like trainability. I kind of indicated that, yeah. But it turns out there's something really nice here that has been shown recently, that some kind of notion of trainability is actually equivalent to decidability of language equivalence. Now, people in different companies and also in different research institutes have looked at other architectures, yeah, like hybrid models of linear RNNs and transformers. So this is like a really big thing that a lot of people are looking at. And finally, I also should mention that we've only looked at text, yeah, but there are also other kinds of transformers, like vision transformers, like speech recognition transformers, and time series transformers that I think are people have not looked at at all. So with that, I thank you for listening, and I guess we have 2 minutes, but I'm happy to answer anything that you have.
Does it work? Yeah. Okay. Thank you for the interesting talk. It's a bunch of interesting work. I have a question regarding. I think sort of this focuses on hard attention. You sort of said that soft attention is quite tricky, and I think you gave some indication as to like what might be different in that context with soft attention, with like a different sort of real world architectures. But I wonder, what would happen if you like take, I don't know, a trained model that is using soft attention, sort of interpret it with hard attention, and then sort of by that you can sort of say, can you for instance translate or compile that model into LCL, and sort of what you get sort of this very discrete, very concrete.
There are some experiments on that, and I must admit I have not really looked at the experimental results, but I know some people who are experimenting on that, and they have claimed that there are some good results, but I haven't really seen them published, so I cannot really give you so much comments on that, unfortunately.
Okay, so maybe in the future we might see some papers.
Yes, yes.
Cool.
Yeah.
Thank you.
Thanks.
Thanks for the great talk. So my question is about the data. So I understand that it's really good idea to capture the class of languages that transformers capture, but when I also consider the training data in the question, then I would imagine that the class would be perhaps significantly smaller? Or for example, can I look at questions about, okay, if this is the kind of training data, then the expressivity is much smaller. Has this been explored?
So if you want to look at, I guess it kind of depends on what you mean by the training data here. So people have looked at trainability, maybe, if that makes sense, but maybe you're looking at something different, not exactly the same.
The motivation for my question is, well, in real life, if I'm using an LLM, then it's a fixed LLM with fixed weights. And I should.
But what you care about is not as in learning, you care about something that generalized. No, I mean, if everything is already in the training data, then it doesn't make sense. So people usually have the notion of at least length generalizability. Yeah. So you want to train it up to, for example, length 100, and then you want to be able to predict consistently up to length 200, let's say. So people have looked at something like that. Yeah. And this is connected to this trainability that I mentioned. Yeah. So there are notions like that, but I also will say that it's also a little bit, the notion is a little bit not very clean so far. So this all, I mean, all the works on this in the last, like, less than 2 years. So, yeah.
Thank you.
Thank you.
No more. So maybe that's thanks, Anthony. So the next talk about it will be about the POPL minimization given by Ori. Okay, thank you.
Great, thank you for the introduction. So I'm Omri, I'm advised by Professor Guy Katz. I'm from the Hebrew University. And in this talk, I will present our project to develop a proof minimization algorithm for neural network verification. And it is a joint project of researchers in the Hebrew University, of Amherst College, and Stanford University. Well, I think at this point, it's almost redundant to say that neural networks are everywhere now, and they accomplish great results in many fields. Some of them are safety critical, but unlike traditional software, neural networks are opaque functions, and even the people who train them, they don't really understand the meaning of the internal parameters. And this combination could be very dangerous because neural networks can behave undesirably. It will be very hard to predict. And of course, this could be potentially dangerous. And what we keep in mind is, as an example, is what we call an adversarial examples. We have a classifier. Is that okay? Okay, that classifies images. And it correctly classifies some images. But if we perturb this image by a little, in a way that the human eye cannot see, then it makes the classifier go wrong. So we would like to ask, well, can we rule out the possibility of error, or at least have some guarantee to find one if it exists? And to address this question, the verification community has developed a variety of verifiers based on a variety of techniques, SMT, abstract interpretation, MILP. So we already have a bunch of verifiers, but they're human-made programs. And as such, they're prone to bugs, to implementation errors. They typically use floating point arithmetic, and therefore, they make mistakes as well. And these mistakes can also be exploited to make the verifiers to get wrong results. And of course, if the verifier is wrong, well, then what's the point on verification? So one might try to verify a verifier. That would turn out to be a very complex task. So instead, what one can do is to enhance a verifier with a proof production capability, as is often done in SAT and SMT solving. The verifier would not only return a result, it will accompany the result with a proof of the result, and that proof could be checked and witness the correctness or reveal the errors made during the verification process. But there are also problems with these proofs. Currently, proofs are eagerly storing lemmas that were learned by the verifier, and that might lead to very large proofs and might be unnecessarily large. It will slow down the checker, it will cause memos. And what we focus on this paper is on an algorithm to analyze this proof in order to remove unnecessary lemmas. It's a process that's also known as unsat core extraction, again, in SMT and SAT solving. And it is doing so by two main processes. First, it removes lemmas that were learned but were not used. And second, it removes lemmas that were used but are shown to be unnecessary. And altogether, it reduces proof size by almost 82%. So this is in general. But before going into depth, we need to cover some background. And I'll start on background on neural network verification. So to formally define the problem, we have a neural network. We define some input property and output property. Then the verification problem is a decision problem of deciding if there exists an input that satisfies the input property, but the corresponding output would violate the output property. And if it exists, we say the problem is satisfiable, and we treat this satisfying assignment as a counterexample, because it's a counterexample for the output property. And otherwise, we say it's unsatisfiable, and we treat it as a compliance of the network with the properties. And many verification algorithms then reduce this problem to a constraint satisfiability problem, as we have in SMT. And for this talk, we will assume for simplicity that the properties are linear, quantifier-free, and that the network employs piecewise linear activation, and specifically ReLU. Even though our work works with any piecewise linear activation. The ReLU function is a very simple function. It's the maximum of the input and 0, and it has two phases. The active phase, which is the identity for positive inputs, and the inactive phase, which is constant 0 for negative inputs. And the result of this kind of reduction that we'll soon see an example would be to solve this kind of constraint satisfiability problem. We would look for an assignment of variables that would be in the kernel of some matrix. It will be bounded from above and below. And there will be ReLU constraints on a subset of the variables. So let's have a look at a simple example. We have this neural network here. It has 2 inputs, 1 output, and 3 hidden neurons. And we have this very, very simple property. Then the reduction to the form that I previously shown you is this kind of, it's in this form. I don't want to go into too much into depth of the technicalities on how this reduction works. It's unnecessarily complicated. But the idea is that this represents the original network and the property. And for example, you can see that each one of the hidden neurons that have the ReLU activation function is broken into 2 variables, the backward and the forward. And that the tableau here, the large matrix, it expresses the linear combinations of the neural network. So for example, B1 is the entry of V1, and it has to be equal x1 minus x2, which are the ones that we see over here. So we will now focus on this kind of problems rather than this formulation, because this will be easier for us to analyze. So you can see that this structure induces linear and piecewise linear constraints. And together, the verification algorithms would search for a satisfying assignment for the linear part, using LP solvers for the linear part, and case-splitting approach for piecewise linearity. And schematically, it looks like this. The verifier would invoke an LP solver. It would search for a satisfying assignment for the linear part of the query. And if it finds that there is none, then there's no solution to the overall query. Otherwise, it will find a satisfying assignment. But then we need to check whether it satisfies the piecewise linear part as well. And if it does, then we can conclude satisfiability, and we have a counterexample in hand. Otherwise, the solver is inconclusive, which means that we might need to split into subqueries. We pick a piecewise linear constraint, break it into its linear pieces. Each piece has its own query with additional linear information, and then we can repeat the process again and again. And that induces a tree structure to the search. We call it the search tree. And note that the query is unsatisfiable if and only if, for each subqueries that we tried, we got into unsatisfiability, because otherwise we would find a satisfying assignment at some point. And one of the main questions that I'm often asked, well, couldn't that tree be exponential? The answer is yes, it could be. It's possibly unavoidable because it's NP-complete problem for ReLU networks. However, it can still be solved in reasonable time, as is often done in SAT. And that's it for the background on neural network verification. I'll continue to proof production, but if there are any questions, I'll stop. If not, I'll continue. Great. So a few words on proof production. First of all, we're dealing with a constraint satisfiability problem. And as such, proving satisfiability is rather straightforward because we can use a satisfying assignment. However, proving unsat is more complicated. And again, we have the complexity theoretical result to ground it. But what we can do is we can produce a proof tree that concretizes the search tree, in which every leaf, every node represents a case split that was done during the verification process, and every leaf corresponds to, has the proof of a contradiction for the corresponding subspace. And now we will cover exactly what each one of the parts here means. But I'll start with how we can prove the unsatisfiability of the leaves. And remember that leaves are proven to be unsatisfiable by the linear part. So we have a classical result from linear algebra in our hands. And specifically, we have this lemma called the Farkas lemma. I'm sure most of you are familiar with. It has many variants. But the variant that we're using is a variant that is relevant to the linear portion of the queries that we already saw. And in this variant, it tells us the following. Either there exists a solution, a satisfying assignment for the variables that satisfies all the constraints, or there is a refutation in the form of a vector such that it creates a linear combination of the tableau that could never be satisfied by variables in these bounds. And not only that it exists, we can also construct it during a verification process. And the idea of using it as a proof is that it gives us a direct result, a direct algorithm to get to the unsatisfiable configuration, even if the solver has explored many linear combination of the constraints. So checking the proof is much, much easier than finding one. And we go back to this example. Again, it is too technical, but we will cover this, this proof of unsatisfiability, this W, and we can see that if we take this vector and we multiply it in this tableau, we get this combination of the variables. And if one wants to check the proof, it generates this linear combination, and then it uses the lower bound for variables with a negative coefficient and the upper bound for variables with a positive coefficient, and it needs to check that it's a negative number. So we could never be in, so it could never be in the kernel of the matrix. And if it indeed it is negative, we can say that the contradiction is correct. So we use this vector in order to prove the unsatisfiability of the leaves. But of course, we're not dealing with a linear problem. We're dealing with a linear and piecewise linear. And as such, there are more complications to that. And one of them is what we call bound tightening lemmas, which are lemmas that are deduced based on bound propagations on the ReLU functions. And those cannot be captured directly by a single Farkas lemma that proves the unsatisfiability of all of them. And instead, we prove them sequentially, one after another. So for example, let's say we have this ReLU connection between these two variables, and we learn as a fact that f cannot be larger than 5. Then it means that we can also deduce that b is not larger than 5 as well. And we can prove it by using a Farkas vector that proves the first result, what we call the invoking bound, and then a proof rule that captures this form of derivation. And after we do so, we can use this as a proof of the corresponding lemma. So we'd have these lemmas as well. So after we have, we cover the lemmas and we cover the proofs of a contradiction, we can have a look at how a proof leaf would look like. It will have a sequence of lemmas learned one after another. And in order to check it, we need to check that, that indeed this vector yields a result that allows us to derive this bound. And then the proof rule is indeed corresponds to a proof rule of a ReLU bound derivation. And we do this sequentially to all the lemmas, and then we're ready to verify the contradiction. So this is how we prove and we check the proof node. And if we go to the proof tree, we need to traverse the whole tree. For each node, it might have its own lemmas. We need to check the correctness of these lemmas. And for each split, we check whether it corresponds to linear pieces of a piecewise linear constraint. And then at the end, for node leaves, we repeat the lemma checking, and we check the contradictions. So we're finally ready to think of proof minimization, because as you can see, it's rather complex structure, and it has it might have too many lemmas that are learned, but are not necessarily necessary. So what do we do? At first, what we try to do is that we go back. We perform a backward analysis that tries to tell us whether a lemma, even though it was learned, it's not really used during proof checking. So we start from the contradiction. We analyze the dependencies of the lemma. We ask which lemmas are used in order to derive the contradiction. And we repeat the process recursively until we reach the input data. So more technically, remember that unsatisfiability is deduced by computing this linear combination, and we need to ensure it's negative. And when we do so, we take the upper bound of variables with a positive coefficient and the lower bound of variable with a negative coefficient, and then we get a number, and if it's negative, then we're done. And note that other bounds that were not used are not really relevant for us. So we start by marking all lemmas as not relevant, and in the backward process, we mark each lemma that we detect as relevant, and delete all the rest. And of course, each lemma has its own vector, so we can repeat the process recursively in a very similar manner. So if we go back to the example from before, we have a proof of a contradiction for our running example. And earlier, we saw that this linear combination uses B3, and B3 has a learned bound using this lemma. And it doesn't use the lower bound of F2 because we only need the lower bound. It's a negative number, which means that the contradiction is not derived by lemma 1. And if we repeat the process for lemma 2, we also see that it doesn't need lemma 1. So we can remove lemma 1 from the proof, even though it was detected. So that's cool, but we ask, well, can we do better? And the answer is yes. The algorithm might include lemmas that are used, but are still unnecessary, because, of course, used does not really mean necessary. And we further use a proof refinement that refines the proof by removing a maximal number of unnecessary dependencies, where the maximal set is defined in a local term. We'll shortly see what does it mean. Again, going a bit more into technical details, what we do is we go back to our computation over there. We compute a linear combination of the variables, and we need to ensure its negativity. But of course, ensuring its negativity, it's not just a matter of a yes or no question, because we can also measure the quantity of the negativity. And the idea is that we call this quantity delta. And this delta could be very far from 0, but the proofs, the lemmas that are used in the proof are not really necessary to this negativity. Even without them, the contradiction would be negative as well. So the idea is to remove the lemmas by their contribution to this negativity to the current analyzed vector. And we remove, of course, we greedily remove them by their ordered by their contribution, and it's a knapsack problem. So we're guaranteed to have maximality in the number of edges that we remove from this directed acyclic graph. So we can go back to our example. And in our example, we're not just ensuring the negativity, we also state that it's -2. And we also state that lemma 2 decreases the value of B3 only by 1. So its contribution is -1. And -1 is larger than -2, so it's not necessary. If we remove lemma 2, the contradiction here would still be with -1. So we can mark lemma 2 as unnecessary as well and remove it in the proof analysis process. And therefore, we're left only with one contradiction without the two lemmas. And it's only the tip of the iceberg. There might be more heuristics for dependency removals to remove more and more lemmas. Some of them appear in the paper. And actually, I think for this, I will not go into too much into depth, but the idea here is that there are a lot of things that we can still cover. So going into evaluation. We've implemented this on top of a neural network verifier called Marabou, which we developed in our lab in Stanford and Amherst College. And we evaluated our method over 6 benchmarks, most of them using the ReLU function only, but other also including different activation functions. And we asked 2 questions to measure the effect, to measure our work. The first is the effectiveness, how many lemmas we removed from the proof. And the second is the performance overhead that was needed when we created this, we applied these algorithms. And this is just one example of the ACAS benchmark, which is very common in neural network verification. On the left, we can see the size of the proof after minimization and the size that could have been if we haven't applied minimization. We can see that the different heuristics that we checked, they didn't matter much, but we were able to remove large percentage of the number of lemmas. And we can also see that there are also a few benchmark examples that we could not have verified without minimization because we got mem outs and so. And on the left, we can see that we have a cactus plot for the running times, and we can see that there is no much difference. And overall, across the benchmark, we saw that between 37 and 82% of the lemmas were removed. For most of the example, it was more to the 80-something%. And the overhead was between 7 and 20% of verification time. So looking ahead, there are 3 main things that we're looking to do. The first is to explore minimization heuristics and see if they are more effective. The second is we'd like to extend the proofs to incomplete methods, so we can use this method for a larger variety of neural network verifiers. And lastly, and this is a thing that we're actively pursuing, is to use this minimization algorithm for CDCL. And the idea is that minimization algorithm is a core algorithm for deriving clauses, and we hope to use that in order to get a meaningful and scalable CDCL algorithm for neural network verification. Then to conclude, I presented an effective proof minimization algorithm that is used in neural network verifiers. And it has relatively low overhead. We have the paper and the code available, which also have an artifact in the submission. And I hope it was interesting. And I'd be happy to take any questions.
Yeah, so I don't know if you've seen, there's this work on kind of verifying the proof verifiers, right, for SAT. I think the KKML has been used for this. So is that something you, how much work do you think that would be to kind of formalize, let's say, theorem prover or something like that to the proof checking?
So it's actually a really good question because it's another project that we're working on, and this is supposed to support that. This work should support this one. It's a difficult task if you want to do it with a new proof checker. But it's something that we managed to do, and it's a collaboration with Heriot-Watt and Southampton University. We published it in the last ITP. But it doesn't support these theory lemmas. And another thing that we could try is to try to convert these proofs into a standard that could be used by, that has its own verified checker, and then use that checker. So that would be another challenge. I think it would not be as difficult. Another interesting point is that this proof minimization makes the checking process much easier. Thank you.
Thank you. I was curious about when exactly this is done, this proof minimization, whether it's done after the verification and the proof is actually produced by the tool, by the verifier, or if it's somehow inbuilt in the verifier and you can perhaps do some more reasoning about it and eliminate some lemmas for perhaps future use and so on.
It's a good question. It's a point it's in the paper, but I haven't touched it. The idea is that we remove lemmas during verification, and we try to do it as early as possible so they won't accumulate. And what does it mean to do it as early as possible? Whenever we finish with a leaf, we can remove the lemma of that corresponding leaf. Whenever we finish with the two children of a node, we can finish with the node, and so on. So we do it, I'll say it semi-lazily, during verification and after we finish the corresponding leaf or node.
Yeah, so it can also help with the memory consumption of the verifier.
Yes, and it does, and we saw that in the evaluation here. So here, it's hard to see here, but we also checked the baseline, and we saw that most of these examples were solved by our verifier with proof minimization, but they weren't solved with the baseline because they reached mem out. And we were generous with memory.
Okay, thank you.
Thank you.
Thanks. For small unsat queries, maybe you can compute the exact optimal minimum. And do you know how close your heuristics get to that?
We haven't tried that. It's very hard to get a small unsat thing. But yes, it's a very interesting question, both theoretically and practically.
this last session of the day. So the first, the session is on modeling, models. And the first talk will be given by Eugène Sancourt from INRIA, and will be on the verification of generic VHDL systems. Okay, so please.
This is joint work with Benoît Boyer and Florian Fessol from Mitsubishi Electric R&D Center Europe. We're interested in hardware verification for critical components. We use the ROC proof assistant to prove some hardware components. So typically, when you do this, you first I don't have a pointer. Okay, you first develop your hardware. We use VHDL. You could use something else. We use VHDL. You do some testing, and eventually you're satisfied with your design. And then you want to write proofs, write properties and proofs in ROC. But of course, in the middle, you need to translate to ROC because ROC cannot read VHDL. So you need some equivalent design in ROC. This also means not only to translate the design, but also have some semantics of VHDL. So I'm interested in this step. Of course, this is not a new topic. So in the literature, people have been verifying hardware using proof assistants. So I would say there are mainly two approaches. The first one, the most satisfying academically and most elegant way, is to design the hardware within the proof assistant, that is within this environment, which means you have a language, you have some formalization properties and so on. And maybe you even have some translation to RTL or even netlist synthesis, which is also proven in your framework. So that's very elegant, but this also assumes that you have hardware developers who are willing to use your proof assistants or your new language. This also means that if you have existing hardware designs, you still need to translate them. So in those cases, for instance, we had existing design, and so in that case you do the second step and the second way, which is either manual or automatic translation, which then you try to justify. So in our setting, yeah, indeed, our target are existing pipeline designs in VHDL, very low VHDL. And we had hardware developers who will not use your favorite proof assistant. So they have their own tools, they know what they're doing, and they will not use something else. So this was given, and our goal was to actually find a trade-off, to use formal methods to have strong guarantees, but also have something feasible within reasonable budget and time. So I want to summarize the steps, a few steps. This is also the overview of the talk, an overview of our work. So you first focus on combinational designs. So the combinational circuit is a circuit that has no states. So there are no registers and no flip-flops. It's really, you give inputs and you get within the same clock cycle, you get outputs. So this is, of course, much simpler. This is a fragment of VHDL. So we developed a translator from some combinational fragment of VHDL to ROC. So this comes with some formalization of the semantics. But actually, this translator makes several assumptions to simplify our work. We make several assumptions, which I will detail. Our translator is not only a translator, it also checks several properties of the design to make sure that indeed we can translate under assumptions. So I will focus on this just in a minute. And just to complete the picture, so then we deal with pipeline designs by reduction to combinational circuits. So we use hardware equivalence checking algorithms, which is basically model checking, to establish. So I just want to give the big picture, and then I will go into detail of several steps. On the left, so we are given a pipeline design. We obtain, so I will explain how we obtain a combinational design, which is equivalent in some sense, and we use hardware equivalence checking algorithms to check that this equivalence holds. And once this is done, now we use our translator to go to ROC, write properties, proof, and so on. So this is the whole picture. Yeah, so okay, the whole thing is our work, but I would say I will focus mainly on these steps, which are maybe our contributions. Okay, so here's what I mean by translating VHDL to ROC. So in VHDL, you can write generic circuits, generic designs. Generic means So here's an entity in VHDL. So an entity is like a signature in VHDL. So you specify E and P, which are just integer parameters, the generics. And given such values for E and P, the entity specifies that this is a circuit with input vectors x and y of size E plus P, and output vector Z and some flags. So this is a floating point adder. And so this means that if you give values to E and P, for instance 8 and 24, then you can synthesize a circuit that will look like this. On the left you have the input vectors x and y, on the right you have the outputs, and so on. So this means that for each instantiation of the generics, you get a different circuit. All right, so, and by our assumption that all designs are combinational, this also means that the circuits are functional in terms of, they define functions that is given values for x and y. You will always get the same value z, regardless of the paths, because there are no states. So this is very good because we use ROC, and we have a functional language, so we're going to map entities to functions. So when we translate from VHDL to ROC, we want a generic translation. So here's what I mean by this. So if the signature of the translated function should look like this, so if you given the float adder entity, we want a float adder function which takes as arguments values for generics, E and P, and then input vectors. And it will output, so this tuple, which is the type of the output signals. So this makes sense. I mean, generics must be arguments of the ROC function because, of course, if you given a floating point unit for floating point operations as an example, of course, you can instantiate for single precision, double precision, or custom precision. And we're going to prove properties of such designs. And we want one single proof of correctness for a generic FPU design. So we do not want to maintain several proofs for each possible instantiation. Yeah, this is not elegant, and this doesn't make sense. All right. So yeah, now I will show how we translate combinational circuits to ROC, and then I will show you why this is not entirely obvious due to, mainly due to generics. But let me start with something even simpler. So VHDL and programming languages are very different in nature. So VHDL basically describes circuits which, if you execute them, compute something. And they do so, I mean, the physical circuit computes in parallel. So you're basically defining gates which will compute in parallel. And of course, ROC's language is sequential and functional. So on the left, you have a really simple circuit with internal signals x and y. These are Boolean signals. And x gets the value of not y, and y gets the value I, which is an input. So in VHDL, the order of these statements doesn't matter because it's in parallel. But the semantics, I mean, if you read the manual, the VHDL reference, they say to simulate such a circuit, you can evaluate in any order. However, you need to start again until stabilization. I mean, I simplify it a little bit. But of course, we know that in the combinational circuit without loops, you can actually go ahead and directly define the final value of each signal. So here, for instance, you first define y, and then define x, because x depends on y. So there's some topological ordering which you can compute it. So this is not difficult. This means that you need to analyze the design, and compute this order. So this is very simple, but it gets a little bit less simple because we have generic designs. So as I said, generic designs describe an infinite number of circuits theoretically, and we only want to translate once. We want one translation that should match the circuit. This means that there should be one common topological order for all those circuits. And is this possible? So I want to show one case where there's no topological order, no common topological order. So you can write things like this in VHDL. So you have here T1, T2, two internal signals. And you can have, so T1, so the first line, the assignment to T1, that's a conditional assignment. So T1 gets the value of A, which is an input, if P is less than or equal to Q. Otherwise, it gets the value of T2. And T2 is quite similar, so T2 gets A. In the other case, Otherwise, it gets the value of T1. So both signals depend on each other, but under different conditions. So there are no loops. There's no loop. But clearly, T2 must be defined before T1 if P is less than or equal to Q, but otherwise it must be defined later, afterwards. So this means if you want, well, you could of course translate to some sequential language, but if you want a really simple let expressions, if you want a simple translation, well, there's no translation. Because there are two translations which you should use in two different conditions on P and Q. So how? Our tool will check this, will detect such situations. So of course, here's how we do. So I've been talking about topological ordering, which means we define a graph, imagine a graph. So we define the edge between statement 1 to statement 2. If statement 1 assigns a signal that is read in statement 2. So below this edge, because y is assigned on the first line, but y is used on the second line. So these edges just show the order of evaluation you should have. But of course, this is not the whole story, because there are the generics. So the condition is that if ST1 assigns a signal that is read in ST2 under some valuation of the generics and loop indices, then you put an edge. So this means with this definition, there's a cycle on the first example, because for some values of the generics P and Q, T2 should come before T1, and for some other value of the generics, the other way around. So you get a cycle. Once you have the cycle, of course, you can detect that there is no topological ordering of the statements. Okay, and there's another example here, so more complex. Below you have a loop, which contains a conditional, and inside there's an assignment to ui. So u is a vector, ui is assigned something. And if you look closely, so ui is assigned between I from 0 up to 9, but also depends on n. And you can see that u0 is assigned here and read on the first statement. So basically, that's why there's an edge. And well, formally, for for some valuation of the generics and loop indices for n equals to 1 and I equals to 0, indeed u0 is assigned in the loop, and it is also used on the first line. So that's why there's an edge. So that's how we reason. And of course, it is possible to decide each edge. You can write a SMT query. That's what we do, guessing the values of the generics and loop indices and dealing with all those conditionals and loop invariants and so on. So I won't show the query, but this is possible. In our case, most constraints were linear. We had a few quadratic constraints, but these were, in most cases, rather small queries, so they were quite fast. Right, so now I want to mention another issue we have in VHDL. So something we dealt with during translation. So in VHDL, I guess also in Verilog, people use, signals have Boolean values, but actually these are not just 1 and 0. You have 9 values for each signal. This is the standard library. This is how you do the things in hardware. So I will not comment on everything, but just to give an example. So this value x, for instance, your signal becomes x if you have 2 statements writing to the same signal. So if you have multiple drivers to a signal, you'll get x. So, and you certainly don't want to deal with 9 possible values when writing proofs. So imagine a binary operator, 9 times 9. So you don't want to do this. Fortunately, we know by the semantics of VHDL that in a combinational design, if all inputs are 0 or 1, and if each signal is assigned exactly once, then all outputs and internal signals are guaranteed to be 0 or 1. So you don't, and then these other values will not appear. So this is a theorem, handwritten theorem by the semantics of VHDL. So this is what we will use to simplify the translation. So we actually check that each signal is indeed assigned exactly once for all generic valuations. That's, again, a bit less obvious than the case with our generics. we need to check that, that there are no multiple assignments, and there's also no missing assignments for all generic valuations. So if this check passes, then indeed our translation our translation will map STD logic signals to Boolean, just Boolean 0, 1 in ROC, which is then much simpler. Yeah. So what do I mean by multiple assignments to signals? So here in this example, you have a vector v of size n, so generic n, and this is a simple simple definition of the values of the vector v. So v0 is assigned first, and this loop assigns values between indices 1 to n minus 2, and then the last value is assigned at the end. So this looks okay, but of course this depends on n. So if n is equal to 1, then you get a double assignment. So if n is equal to 1, then the loop doesn't get generated, it just disappears, and you have v0 equals to 1, v0 equals to 0 at the last line. You actually get x. So this is typically a design which we reject. So if you want to translate to ROC, then you need to work on it again and give us a better design. Yes, again, I'm not going to show you the query, but again, we write this SMT query to check this. So basically, we go over all pairs of statements writing to the same vectors and check if for some values of the generics and for some loop index values, is it possible that they write to the same, exactly the same signal. Okay, and once such checks are done, I just want to show just a few examples what the translation looks like. So we have already seen this. So such simple statements just become let expressions, giving the final value, stabilized value. Because all entities are functional, when you have component instantiation. So component instantiation means given another entity, you can of course instantiate it, which becomes a subcircuit in your circuit. And so subcircuits, subcomponents just become function calls because we know that the other file, the other entity is also a function. So then the translated function just looks like this. The full adder function just calling the half adder function. We have our own little library for vectors. For instance, a vector assignment to value v of 0 looks like this. So I just showed the syntax, but we have an operator that defines a new vector out of existing v by just modifying the 0th element. So the expression on the right defines a new vector, and then we just, with the let expression, we just overwrite the name v. So if you have several assignments, v0, then v1, and so you'll have let v something, and let v something, and let v something. And then for generic loops, of course, in the functional languages, you don't have for loops, but you have iterators. So this is like something like a fold left operation. So the n.iter will iterate the given function n times, starting from you give the initial value you give to this function is the current values of signals. And the function will just emulate the one iteration. It will just compute next values and return next values. Okay, so this is just how you would encode just a for loop in a functional language. Right. So my point here is that I think the translation is quite simple. I think it's as simple as it could be, and this is important because then we write ROC proofs, and of course, if your translation is very simple, then this is much less effort. So the overall tool looks like this. We have VHDL. So we rely on several open source tools like GHDL for parsing, and so we let GHDL build the syntax tree, and we just analyze. We do our checks on the syntax tree. So I mentioned partly the unique assignment check. We do other analyses like we check array bounds. Again, array bounds can be violated for some generic valuations, but not for others. So this is again with SMT. And we also check for integer ranges for integer signals. and overflows and so on. And we can also check dead code. So there are many analyses that are done, mostly with the same ideas I presented. So if all those checks pass, then we try to compute the topological order. And then we can translate to ROC. So basically the tool can be also used as a linter verifier or whatever for VHDL. So we have a nice plugin that will tell you the errors, and that will also give you, thanks to this empty solver Z3, for which values of the generics you have an issue, whether you have, like it points to two lines that try to assign the same signal and so on. So it will help you develop VHDL that can be then verified, that can be translated. And then eventually you translate to ROC. Right, so that was for combinational circuits. Now I want to show how we deal with pipeline designs. So this is, again, this was the big picture. So I will talk about the left part here. So what is a pipeline circuit? So let's start with a combinational circuit that looks like this with a few gates. Again, combinational means that given inputs A and B within one clock cycle, you have stabilization, and at the end you can read the output. And so you could pipeline such a circuit by adding registers, so shown in blue squares. So you could put registers, so register will just delay the computation for one clock cycle. So adding such registers means that you're doing the computation like shown in here in 3 steps. So at the first step, so the given inputs A and B, so all the gates will stabilize. I mean, for this part will be computed, and then we will wait for the next clock cycle. And next clock cycle, all these values are correct. And at the 3rd clock cycle, you can read the output. So this is just about delaying the computation. And we restrict for now to simple pipelines. What I mean by simple pipelines is that between each input and output, you have the same depth of registers. So that is the same pipeline stages. This, in practice, this means that we're interested in components of a bigger design where you have the same pipeline depth. Okay, our problem was the other way around. So we start with pipeline designs, and now we can only analyze combinational circuits in ROC. So what we do is that we start with the pipeline design, and we remove the registers. We can just syntactically remove and short circuit the registers. You get something combinational, which then you can prove. You translate to ROC and prove. So of course, yeah, this is easy to do, but then the question remains, so these 2 circuits are supposed to be equivalent. Are they really equivalent? And what you could also do something in between. So what we do, we do remove the registers, but then you can also change a little bit, a few things. For instance, if you have unsupported VHDL constructs, or if you know that some small components will be proven easily, if you rewrite it, you can also change stuff. So this is more or less what we do. So basically, we have some alternative combinational circuits done manually, and we think that this is equivalent to the pipeline design. So what we do, so the picture looks like this. We have pipeline design. We remove registers, maybe we tweak a little bit, you get a combinational design. And so we want these to be equivalent in the following sense. So for all inputs, for all primary inputs, the pipeline circuit must output after k clock cycles what the combinational circuit outputs in one shot. So this is the intuition, because the pipeline circuit just delays the computation. This is what you want. And you can check this with, we don't check this with proof assistance, we check this with model checking or hardware equivalence checking algorithms. So just to show you the idea, we synthesize a netlist from the pipeline design. And then we just disconnect the registers, and we get a combinational circuit netlist that looks like this. You have the inputs and outputs, and then because you disconnected the registers, now the current value of the register now is an input. So if you give the input as an input the current values, then you can read the outputs and you can read the next state values of the register. So this is a really simple syntactic operation. Once you do that, you can then make several copies, and connecting the next state values to the current state value. So this is really the unrolling and bounded model checking. It's the same thing. And then you can compare this with the combinational design. Now you have two combinational circuits, and there's a literature over 30 years or maybe more comparing combinational designs in hardware verification literature. So that's what we use. So to show the final picture and the tools, so from the pipeline design, we use tools like ABC, YOSIS and ABC, open source tools, to synthesize a netlist, which we then unroll. And the combinational design, we also synthesize it to a netlist and then check with ABC or also YOSIS and other tools. We check their equivalence. And this is how we establish, this is satisfactory for us. So we think that then the pipeline design is equivalent to the combinational design. And then with our translator, we go to ROC and write proofs and so on. And yeah. Okay, so this, should I stop or no? Okay, this is the full picture. I mentioned a few things, but as an application, one of the applications is a generic floating point unit verification. And the details of the case study will appear maybe hopefully later. So this is not in the paper. Okay, and I'll let you read. I don't remember what I wrote.
Thank you.
So I'd like to ask about, so you talk about the verification of pipeline designs, and so what's the main difference between like general sequential circuits with one clock domain and the pipeline design? Because when you are doing the unfolding, you can pretty much do the same thing for sequential circuits, no?
You could do for sequential circuits. That's how you verify sequential circuits. But what we exploit here is that once you unfold for a finite number of steps, then you really get something equivalent. That is, although a sequential circuit, it's like computing something with registers, you can unfold it, unroll it, but it will not be, you'll get a combinational circuit, but it will just represent the computation over bounded number of steps, right? So you might not get something completely equivalent.
Okay, so you counted that like you have a finite number of steps, and then you get the thing which is equivalent to the non-pipelined. Right?
Yeah.
Okay.
What kind of top-level specification do you verify against?
Could you say again?
What kind of property are you proving at the top level in ROC?
Oh, in the FPU or?
Yeah, or in the FPU case or in the other.
The goal would be to prove, so given we had some open source design, FPU, and the goal is to show that each operation conforms to the IEEE 754 standard, which is, we have some formalization of these properties, and we show that these match.
Yeah.
So
you verify at the block level, so you have a floating point adding block, and you verify that the input-output match.
Yes.
Yeah. Okay.
Yeah, exactly.
Questions, please?
Thank you. Thank you for the talk. You were restricting like the different possible values for the different circuit gates to only be 0 or 1. Are there any input circuits that are of interest where that actually isn't possible? Where there might be an X value in, but you actually still, that is, as technically speaking, still a valid circuit you wanted to prove?
Well, these values are used, right? But I think that they're used in simulation, and in synthesis, I don't exactly know what they become. So in multiple drivers, so this depends on the options you select, I think, during synthesis. Yes, if you want your specification to talk about these, I guess yes, but I'm not sure exactly what Z or X or undefined or this, what did they become their synthesis? Because eventually, I didn't talk about synthesis, but eventually you want to synthesize to circuit or to FPGA, and then I don't know how to link what would happen, what what does X mean in the FPGA? So I don't know that. So
thank you.
Last short question.
Hi, thanks for the talk. So you explained how to prove the equivalence of pipeline component, but do you need to, like by unrolling the circuits multiple times, do you have to do that for every output, or do you have a restriction that all outputs have the same depth?
yeah, they have the same depth, and we by hypothesis for now, I don't know, remember. Yeah, yeah, whatever the inputs you give, you're going to read the value after k steps, k clock cycles, for all output bits, right? So that the depth is uniform, whatever the operation you're doing on the circuit.
Okay.
So really, after k steps, you'll get your value. So yeah, we just unroll once, and that's yeah.
Okay, thanks.
Okay, so let's thanks the speaker. The next talk will be about the semantics of Promella, and it will be given by Byung-Gu Son. Sorry. Teach me how to pronounce it.
Okay. Thanks for the introduction. My name is Byung-Gu Son at Postec. Today, I'm going to be presenting our work on formal executable semantics of Promella, which is a very widely used model checking language. And this is joint work with Kyungmin Bae. So I guess many of you have heard of the SPIN tool because it's a very widely used tool for modeling and verifying concurrent systems or distributed systems. So Promella is the input modeling language for the SPIN model checker. So the workflow is that SPIN takes Promella code as input. It parses that code into an automaton, and SPIN performs LTL model checking on top of this automaton. Some good things about SPIN is that SPIN works fully automatically and very efficiently. And another good reason to use SPIN is that it provides a very intuitive high-level modeling language, Promella, which has a very similar syntax to C. So it's going to lower the hurdle for modeling for those who's already familiar with C. And so the tandem of Promella and SPIN has been very successful in the past few decades. It has been used in many real-world domains like cryptography protocols, Linux system calls, and many others. And the SPIN tool has received ACM Software System Award in 2001. However, there are limitations as well. The one problem is that SPIN only supports explicit model checking, which basically means that SPIN performs model checking by enumerating all the reachable states of the system. And therefore, it cannot verify properties for systems with infinite number of states. And this is very hard to remedy with deductive reasoning because there is no prior work for formal semantics that is aimed at code-level deductive verification. There are a bunch of work that provides the semantics, but most of the work focuses on translational semantics that translates Promella into the automaton. So all the high-level constructs of Promella gets parsed away. So Promella has no role in the analysis stage, which misses out a lot of opportunities to exploit state-of-the-art program verification techniques on top of Promella. So to overcome this limitation, our goal is to define an executable semantics of Promella. So by executable semantics, I mean a semantics that is almost like an interpreter by itself, so that you don't have to implement yet another interpreter. And then with this executable semantics, we aim to mechanize the semantics in a machine-readable framework. This will enable automatic generation of related tools like model checkers, state space explorators, and many others. In particular, we're interested in deriving a code-level deductive verifier for Promella programs. And hopefully, this will enable a wider range of analysis of existing Promella models used in the industry and academia. So to give you a little background of POPL', as you see in this example, POPL' code consists of declarations for concurrent processes. So here you have the declaration for P1 and P2. And at the top of the code, there are declarations for the channels and integers. And there are two types of channels in POPL'. One is handshake channel, and the other one is buffer channel. So for example, in this code, P1 is the sender of the handshake channel, and the process P2 is the receiver of the handshake channel. And this handshake channel is meant to be executed in synchronization, so the two operations are executed at the same time. On the other hand, there are buffer channels. So P1 is the sender, and P2 is the receiver. And in contrast to handshake channels, the sender does not have to wait until the receiver is available, and vice versa for the receiver. So this buffer channel is used for asynchronous communication between the two processes. So the intended behavior of POPL' program can be understood as execution traces, which are sequences of atomic actions like channel operations. So an example of execution trace may start by the process P1 that sends a message to the buffer channel D, followed by process P2 that receives the message from the channel. So it's going to receive the message that is sent by the process P1 in the prior step, and then execute the remaining fragment of code, so on and so forth. So up to this point, we have this interleaved sequence. One exception is that of handshake channels. So handshake operations are meant to be executed at the same time. So this is the intended behavior of semantics, behavior of POPL' at the language level. And one more remark that I want to make is that each of these basic actions are meant to be executed atomically. So for example, this increment statement is meant to be executed atomically, which is not necessarily the case in other languages like C. A POPL' code may contain non-determinism, like the if statements and the do statements in the code. So if statements are for non-deterministic selection, and do statements are for non-deterministic repetition. So essentially, do statements are repeated if statements. And this kind of constructs can also be found in many other related formalisms like Dijkstra-Scotted command language and many others. And another central notion is that of enableness. And enableness is really important because it determines when a certain statement can be executed, and it also determines when a certain non-deterministic branch can be selected. For example, to check if this second option of the outermost if statement is selectable, you have to check whether the guard, which is the whole do statement, is enabled, which again is reduced to the individual enableness of the inner structure. So in particular, you have to check the enableness of the, for example, the channel receive operation. And this is the channel receive operation via the handshake channel. So you have to ask whether there is an enabled matching partner in some other processes. Okay, so this shows that checking for enableness is quite complicated. And so we're essentially doing a proof search over each non-deterministic point and for each concurrent process. And it involves a very heavy computational, conceptually computational steps for doing the proof search before checking whether a one-step intended execution may be fired. So the problem is that this kind of proof search steps gives rise to this strict dichotomy between structural rules and operational rules, where the structural steps in the vertical axis corresponds to implicit proof search steps, and which is not captured by the operational steps intended by PROMELA at the language level. The reason why this is problematic is because the operational steps does not specify concretely how to perform the proof search. So this is problematic when, as far as executable semantics is concerned. So the challenge is to design an executable semantics that is as concrete as an interpreter, so that you don't have to implement yet another interpreter. And this kind of executable semantics will not include any structural reasoning for each one-step execution. So it's going to be flattened like that. And our approach to tackle this challenge is to represent PROMELA programs as continuations of computational tasks. And this approach is inspired by continuation-based semantics, where typical sequential programs are flattened into sequences of computational tasks, so that every internal computational steps are represented explicitly. So this kind of continuation can be read as first do the step A, and then do the step B, and then do the step C, and so on and so forth in the linear structure. So our approach is to generalize this representation for computation so that the continuation can be forked to capture the non-determinism in each process. So here, each of the computational tasks may encode the proof obligations as special cases. Further extending this approach, we can also represent the non-determinism under concurrency. So a system of concurrent processes with non-determinism can be represented explicitly as a forest of forked continuations, where trees correspond to concurrent processes, and each of the branch in the forked continuation corresponds to individual non-deterministic options in the if statement. So this will correspond to a whole specification of the PROMELA program. So based on this representation, we propose a semantic pattern called load and fire, which captures the interplay between the steps for proof search and the steps for actually firing the execution. So the loading rule defines how to perform the proof search. So for example, if we have this if statement, the proof obligation for the if statement at the leaf of the continuation, the load rule will decompose that proof obligation into multiple proof search sessions and explicitly represent it in the representation level. And then fire rule comes into play. It's going to discharge each of the enableness condition at the leaf. And at the same time, it's going to fire the side effect. One example of such side effect is that of making a non-deterministic choice, so that when the fire rule applies, the forked continuation gets collapsed back into the linear form, which reflects the fact that the non-determinism has been resolved. So let me give you a concrete example. First, the loading rules can be used to define the semantics of if statements, where the loading rule for if statement says if we have this proof obligation at the leaf of the continuation, what you do is you simply decompose this proof obligation into two separate proof sessions, where the upper one corresponds to one particular non-deterministic option in the if statement, and the proof session at the bottom corresponds to the rest of the options. And similarly, we can also define the semantics of do statements, which is non-deterministic repetition, by a load rule that says if we have this proof obligation for do statements what you do is you simply attach to it the another proof obligation for the if statement. So this kind of description is, this coincides with the imperative interpretation of do statements, that do statements are basically repeated if statements. So to demonstrate how these load rules and fire rules work together, here's a concrete example. So this snippet of code is the one that we saw in the previous example for the process P2. So initially, the outermost if statement will be represented as a proof obligation like this. So this is the continuation of the initial state. And then the loading rule will apply to the if statement, so that the continuation will be forked like this. So the upper branch will correspond to the branch 3 in the code, and the lower proof section will correspond to the whole do statement in the code. Now, the loading rule for the do statement will apply, which simply attach in front of it a new proof obligation for the if statement. And again, this will be decomposed by loading rule to decompose further like this. And now we have all the proof obligations decomposed. So if you assume that the buffer channel D is non-empty, which means that that the channel receive operation at the leaf node is enabled. So this is the timing where fire rule comes into play. So it discharges the proof of this atomic action, and at the same time, it makes a non-deterministic choice, collapsing the continuation back into the linear form. And as another example, this is the complete version of the previous example, where we have 2 concurrent processes. So the 2 concurrent processes will be represented as the forest of 2 continuations initially. And by sequentially applying the load rules in the fully loaded form, the forest will look like this, where each of the branch is decomposed. And the result is that now it is clear from the context of non-determinism that the handshake operation is enabled. So this can be checked by the fire rule by a simple syntactic matching. So you don't have to go through structural reasoning at each step. So the fire rule comes into play. It discharges the pair of proof obligations, and it makes non-deterministic choices over the pair of continuations. Now, to summarize our approach, our pattern of load and fire, we had these loading rules that bring the proof search explicitly represented into the semantics level. And then the fire rule will fire without structural reasoning, because it's going to be, because the structure has been flattened by the loading rule already. So alternating the 2 stages step by step will give us the executable semantics as desired. So based on this semantics design, we mechanized our semantics of POPL'26 using the K framework, which is a semantics definitional framework based on continuations. And we formalized most of the core features of POPL'26 in the K framework. And it turns out, by design, semantics in K is highly executable. And the K framework exploits this executability to automatically derive related analysis tools like model checkers, deductive verifiers, and many others from the semantics. And it has been used to successfully specify the semantics of many programming languages like C, Java, and so on. And in particular, we use the model checker given by K to empirically validate our semantic definitions of POPL'26 by comparing the outputs obtained by the original spin implementation and the model checker. And again, we use the deductive verifier given by K to formally verify POPL' programs. So our case study includes using this deductive verifier to formally prove invariant properties for distributed systems. And it turns out sometimes the deductive verifier obtained by K can be more powerful than spin is. And we demonstrated that this is the case for proving mutual exclusion for Lampert's bakery algorithm, which has an infinite number of reachable states. And as a result, this example is not verifiable by the spin model checker. But this is verifiable by our deductive verifier. So Lampert's bakery algorithm is a distributed mutual exclusion algorithm proposed by Leslie Lampert. So this is the code of bakery algorithm written in POPL'. So we have two declarations for processes. And each process goes through 3 stages. So first, each process gets the ticket from a global counter. And as a next step, when the ticket number gets called, it gets into the critical section. And then after that, it can exit the critical section non-deterministically, and it gets repeated over and over. The result is that the ticket number can grow indefinitely, inducing an infinite number of reachable states. So spin cannot verify this POPL' program. And we verified the mutual exclusion for this bakery algorithm using deductive reasoning. So we annotated the bakery algorithm code with preconditions and postconditions. So under a reasonable precondition, our postcondition asserts that asserts the invariant that the number of processes in the critical section is always less than or equal to 1. The result is that the deductive verifier by K can automatically verify the specification within 5 minutes. As a side note, we used some auxiliary specs to aid the reasoning for the deductive verifier. So to conclude my presentation, we designed an executable semantics of POPL', which is enabled by the semantic pattern, load and fire, based on the forked continuations. We mechanize the semantics in the K framework, which opens the door to code-level deductive reasoning for POPL' programs. And also we demonstrated that our deductive verifier can verify systems with infinite number of states, which is out of spin's capability. Future work includes extending this deductive reasoning to temporal properties like LTL logic, which is outside of which may be outside the scope of the invariant properties that we covered. Another interesting direction would be to extend the case study for parametric models to allow arbitrary number of processes. Okay, so this is the end of it. Thank you very much.
So there is place for some questions. So please, Anton.
So maybe just a quick question. So can you also do liveness now, or just?
You mean liveness?
Yeah. Can you also verify liveness now?
Not yet.
I mean,
not
really?
Yeah. We cannot do temporal logic yet, so
okay,
it's
so
future work.
You can't really do it yet. All right. Okay.
Okay.
I have one by waiting for that. So you say that you have this project of doing parametric verification, but I mean to introduce infinite number of parameterized number of processes, for instance. But you have sometimes in deductive verification, there were some work on reducing the parametric problem to some finite problem and
like
so on.
cutoff techniques.
Yes, so
like
taking the small model or thing like that. So will you think that it will be possible to do these such proofs in your system somehow?
I'm not so sure about that because we haven't really started that, but I think that would be a very good.
Because you have already the deductive verification engine somehow for the computing these traces, so then you have only to.
Actually, our proof system for this deductive reasoning is based on what's called reachability logic, which is a particular proof system by the K framework. So I'm not really sure if that allows that. So we'll have to look to that.
Okay. Other question?
Just one more question. So do you have any other example other than this bakery protocol, or
So
is this the only one?
This is the only non-trivial example. We have some trivial examples, but yeah, this is the only non-trivial example covered in our paper.
So for the bakery, you mentioned that there were also some auxiliary, what was it, specifications? So can you elaborate on that? What exactly did you need to provide in addition?
Yeah, so this has to do with the fact that the reachability logic, which is the base, the proof system that this deductive verification is based on, and auxiliary claims are only of technical interest. So I think in principle it works automatically at the conceptual level, but the framework, the toolchain of K framework, it does this deductive reasoning by somehow enumerating symbolic states, but the problem is that it does not maintain all the intermediate states by for efficiency issues, memory issues. So these auxiliary claims is to somehow it's related on the fact that how to say, the reason why we have to use this auxiliary spec is because the implementation of this deductive verifier does not maintain the internal states. If it maintains it, then we don't need it.
Okay. And maybe one more question. So you assume, so in your bakery example, so you assume the counters to be unbounded precision, or is there? I'm not an expert in Promula, but I thought there is some like bound on the size of the integers or something like that.
In the syntax of Promula, there's you cannot specify for arbitrary number of processes, but yeah, we have to relax the syntax in order to do that.
Yeah, but about the precision of the integers there, because you have the counter, right? You have so if you have bakery, you have somebody who is counting the current ticket, right?
Yeah.
And then, like in Promula, is the integers there are bounded size, isn't it?
Yeah. In Promula, it works like that.
So is the bakery does it take care of the overflow or underflow or something like that?
Actually, that's the issue that when we're using the spin model checker, but because we're not using the spin model checker, we're not interested in that.
So you still have time for one question? Okay, so I have one. So there are other attempts to give formal semantic for Promula, for instance, in Isabelle and.
Yeah, I know that. Yeah.
So how you compare with this work, for instance?
Isabelle.
Hall.
So if I'm correct, that work is about translating Promula into automaton using Isabelle.
So it's foundation, yes. So the semantics, it's also semantics of Promula.
So the semantic style is really different.
The translation, it's okay.
Yeah. So we're not. So it's directly translating the Promula model into an automaton. So yeah, the Promula constructs are parsed away. Yeah. So but yeah. So we cannot apply code level deductive verification on top of that. Yeah, so that is the problem.
Okay, so let's thanks the speaker again. So the last talk will be given by Kenneth Rogael on the efficient discovery of actual causality in stochastic systems. It's fine.
All right, thank you for the introduction. Today I'm going to be presenting the efficient discovery of actual causality in stochastic systems, and this was done also alongside my co-author Arshia and our advisor Borzu. So why do we care about causality? Well, in a lot of cases it can help us understand why particular cases fail. For example, one of our running examples is a mountain car that is stuck in a valley, and its goal is to reach the top of the hill on the right-hand side. And if it does so within the allotted time, that's considered a successful case. However, if it does not, then that's considered a failure. And we're interested in trying to explain what led to this failure. However, many cyber-physical systems operate in more stochastic environments, subject to noise and disturbances. So accelerating in the same position in two different runs might not necessarily lead in the same next state's position. And identifying the cause of such specific events in stochastic systems can be quite difficult. So the notion of causality that we're interested in is called actual causality, and it's proposed by Halpern and Pearl, and that's specifically looking for cases in the token case, which is this specific cause, or sorry, this specific failure was caused by this specific cause. For example, for the mountain car, why would it fail to reach the destination in that particular case would be such a question. And this definition, however, is limited to only non-probabilistic cases. So in order to handle stochasticity, we need to work with a different notion introduced by Fenton and Glenn, which is an extension to AHC called probabilistic actual causality. In order to model such systems with noise, we chose to use discrete time Markov chains. And we can consider these to be acyclic in our case, as since we treat time as a variable, cycles are not possible, since two states at the same position occurring at different time steps are considered distinct. As you can see at the bottom, every time there's a transition, t also increments. And each path in this DTMC represents an experiment, and the probabilities reflect the frequency of the occurrence. And success and failure states are absorbing states, as we don't really care what happens after that for our purposes, and we are going to label these as halt. So what we did was we applied this notion of probabilistic actual causality and adopted it to work with discrete time Markov chains. We formulated the discovery of these probabilistic actual causes as an SMT problem. And finally, we applied an abstraction refinement technique in order to handle larger model sizes. Probabilistic actual causality specifically calls for two different constraints, first of which is rather intuitive, and that's simply that there is a scenario that occurs where the cause occurs and then afterwards the effect occurs, and that's going to be considered the actual world. And the second constraint is a little more complicated, but it says that for any counterfactual scenario where the cause does not occur, but the effect does, and all variables within the contingency W agree between the two, the probability of the counterfactual world must be strictly lower than that of the actual world. For example, if we were to select this state as our cause and this state as our effect, it would take a distribution something like this in order to make a PC2 hold. And in order to formalize this for DTMCs, we're going to use hyper-PCTL. And starting with the actual world, we're going to formulate it as this, saying that there is a cause that occurs and a subsequent effect eventually occurs. However, we also want to specify that there's no effect that happens before that cause, and we are interested in the probability of this case happening. For the counterfactual world, we are going to encode it such that we don't want to see the cause until we see the effect. And then, as in PC2, we want to ensure that the actual world happens with greater probability than that of the counterfactual world. And for the contingencies, we want to say that for all variables within the set W, they agree between the actual world and the counterfactual world. Sorry. And that's going to hold with probability 1. And finally, we want to say that there exists an actual world that the probability is greater than all counterfactual worlds. For example, if you take a look at this DTMC, which represents the mountain car example from the beginning, and we want to reach a goal of at least 0.6 on position, each state's going to have a position, a velocity, and an action. Here you can see is our initial state at time 0. And at the bottom, you can see that there's going to be 5 different absorbing states, 2 of which are considered phi e, or effect, as they do not reach the goal position within the allotted time. And using our definition, we can find that S1 can be identified as an actual cause of phi e, as if we evaluate the actual world, we get 0.345, whereas for the counterfactual world, we only get 0.15. Also, for this case, since W is empty, we can trivially satisfy the contingencies. As for the problem we want to answer, is given a DTMC representing our causal model and a predicate, phi e, representing our effect, can we find a phi c such that it satisfies our definition of PEC? In order to do so, we encoded it as an SMT problem, and we'll go through this step by step. For the actual world, we are going to create a variable for each state, and we're going to assign that to 1 if the state is in the cause, and if its reachability to the effect is greater than 0. We're going to set it to 0 if the state is not in the cause, and the state is either halting or in the effect, or if the reachability from that state to the effect is 0. And finally, for all other states not in the effect, we're going to propagate these values backwards through the transition system. Now, to calculate that reachability of effect, we also are going to define another variable for each state, in which it is going to be set to 1 if the state is in the effect. It's going to be set to 0 if the state is not in the effect and it's halting. Or otherwise, once again, we're going to propagate the other values through the transition system. Moving on to the counterfactual world, we are once again going to define a state variable for each state representing this probability, and we're going to set it to 1 if the state satisfies phi e, 0 if the state is not in the effect and it is halting or in the cause. And otherwise, we are going to propagate the probability through the transition system for all states that are not in the cause. Now, in order to encode the contingencies, we are going to require stutter trace equivalence for W, as the differences in sampling times between the actual world and counterfactual worlds might not be the same always, but that doesn't mean that we can't reason against them. And in order to encode that, we came up with this formula where we say that for all pairs of paths in the model from the initial state to a halting state, they must be stutter trace equivalent. And in order to encode that, essentially what we do is we partition each trace into a number of contiguous blocks in which we require each state to be equivalent on W for every variable within W. And this first term says that the first states of each of these cuts is going to agree on W with each other between the actual and counterfactual world. And then for each state in each block will also agree with the first state in its own block. However, this does not necessarily work well for larger models. In some of our test cases, we have about 6,500 states, and it takes longer than an hour to solve. So we needed to use other techniques to handle more realistically sized models. In this case, we chose to use abstraction refinement. And when we abstract our DTMC, we end up grouping multiple concrete states together into one abstract state. But that introduces a new source of non-determinism, as when we're transitioning from that abstract state, how do we know which distribution to use? So the abstract model ends up becoming a Markov decision process where each concrete state transition becomes an action. For example, if we were to have these three states here and we wanted to group them together into an abstract state, we would end up with something like this, where each one of these concrete states is going to have an action. And for example, since state 1 only goes to other states in the abstract state, is going to loop on itself, whereas the other two are going to remain as they were before. In order to handle our abstraction refinement, we are first going to introduce a predicate abstraction, which we come up with a set of predicates which we apply to the DTMC in order to group it into a number of abstract states. Next, we're going to apply an SMT solver to identify potential causes within this new abstracted MDP. And finally, if no cause is identified in the abstract model, we're going to refine that model by partitioning one of the states that we have into a new set of concrete states. And the algorithm will terminate once either a cause is found or once the abstracted model is fully concretized back to the DTMC. For example, going back to the mountain car example, if we were to come up with predicates such as this on velocity and position, the resulting abstracted MDP would be this, where you can see the halt states are grouped together, particularly the failure cases are grouped together. But if we were to apply our SMT solver to this abstracted model, we would not actually be able to find a cause. So if we were to select state S hat 1 and choose that to refine it, we would end up breaking that into its constituent states. And then we would end up running our SMT solver once again. And then in this case, we would actually be able to identify S hat 1, as an actual cause. However, once we're working with MDPs, our original encoding no longer works for the SMT solver. So we need to also adapt our encoding for that. So just quickly going over the previous encodings and how we updated them. We're interested in minimizing the probability for the actual world and maximizing the probability for the counterfactual world so that we can guarantee that PC1 and PC2 still hold. For reachability of the effect in the actual world, we simply select actions as to minimize this probability through the MDP. Likewise, for the actual world, once again, for the overall term, we are going to minimize the actions that we take in order to minimize the probability. And finally, for the counterfactual world, we are going to select actions as to maximize the probability of the counterfactual world. However, when we're working with abstraction, we also need to consider how we're handling our contingencies. And we consider two different options, the first of which is going to be subgraph enumeration, where we look at all pairs of subgraphs in which all traces are stutter equivalent with respect to W, meaning that we don't have to worry about W in that case as long as we make sure the subgraphs agree on it. Or the other option is we can look at W preserving abstractions, where we require the abstraction function to preserve the equality of the computation trees with respect to W, and in order to do that, we would have to encode it as follows, where this simply says that all pairs of schedulers in the set of finite schedulers, and for all paths from initial to halting in the induced DTMC, are stutter trace equivalent. Additionally, when we're looking at refining states in our abstraction refinement, we also need to choose which state to use in order to break up into its concrete states. And the first option we have is choosing the state with the highest number of actions, meaning it contains the largest number of concrete states. And the other option we have is by selecting the state with the largest range of reachability to the effect. In addition to our mountain car example from earlier, we also have two other case studies, the first of which is a lunar lander, which is a 2D moon landing simulation that has a number of variables, and the goal is to safely land between two positions on the ground and also without tipping over. If failure here occurs when the lander either tips over or does not land at the designated area within the time frame. Our other case study is a little more complicated. It's an F-16 flight simulator, which models the outer loop controller of a fighter jet with two different test scenarios. The first one's going to be an engine test, which simply tries to achieve a target velocity. And the other one is going to be a climb test where it attempts to reach a target altitude within the allotted time. However, both of these also are subject to a number of different safety constraints, such as G-force or angle of attack, and failure occurs when the target is either not reached or one of these safety constraints is violated at any point. If we were to look in detail at one of the cases that we did for the second scenario of the F-16, so the altitude one. In this case, our goal is to reach an altitude window of about 1,400 feet, plus or minus 50. And our algorithm was able to identify this particular state as a cause. As you can see, all four of the states that it reaches from there actually are failures, as all four of them violate the G-force constraint. And additionally, two more of them are also unable to achieve the target altitude. If we were to look at the counterfactual world, so the alternate states that it could have taken instead of those, we can see that almost all of them are able to achieve the goal after a certain number of steps, except for one, which ended up violating the G-force constraint once again. So it's rather clear that with the actual world having a probability of 1 that is quite greater than that of the counterfactual world in this case. Now looking at more results from the other case studies that we did. This column here can show you the size of each experiment in terms of the number of states in the DTMC. This column is going to give the timings for the concrete DTMC solver, the original SMT encoding. And then these two columns are going to give you the times for the MDP solver. And the one on the left is going to be selecting the state to refine with the largest number of actions. And the value on the right-hand side is going to be when we select the one with the largest reachability range. As you can see, most of these cases, the abstraction refinement method greatly outperforms that of the concrete. However, if the model is sufficiently small, then the overhead induced by using abstraction refinement outweighs the benefits, and in these two cases, the concrete model was slightly faster. For the F16 scenarios, you can see as the models get larger, especially on these, the benefits of using the abstraction refinement are a lot greater than that of the concrete solver. So reviewing what we covered, we formalized probabilistic actual causality to work with DTMCs. We applied an abstraction refinement technique that is compatible with PAC for DTMCs. We formulated an SMT problem for both finding actual causes in DTMCs and in MDPs. And we saw that based on our experiments in 3 different case studies, the performance is much better for the abstraction refinement as compared to the concrete one. As for future work, we're also looking at how we could do this when the original system is an MDP, so we can also handle non-determinism in addition to stochasticity. Finding causes in POM DPs, investigating performance for reinforcement learning, and large language models for discovering actual causes or for probabilistic actual causes. And finally, for finding the actual cause of out-of-range outputs from neural networks in interest of finding how we could repair them. All right, thank you.
So there is a large room for questions, please. Okay, let's see.
So you're doing this reduction to SMT, so what particular SMT theory are you reducing to?
I'm not sure, I'm sorry.
So you just say anything, or?
No, sorry, my co-author.
Okay.
Yeah, sorry, he's the one that worked specifically with that part.
Okay.
I can probably answer. So it's the integer linear arithmetic with uninterpreted functions. So we specify no, with quantification. Yeah, because the actual world is existentially quantified, the counterfactual world is universally quantified. And we specify the effect as a predicate, and then the cause as an uninterpreted function where the interpretation gives you the predicate for cause.
Okay, and maybe one more question. So which solver are you using?
We're using Z3.
Z3, okay, thank you.
So just a quick follow-up question. So if it's a KF-LIA, so what's the plus for? Do you use plus for what again?
Sorry?
No, I think I'm asking you.
Oh, I'm sorry. Yeah.
So if it's reduction to QF Lia, right? So so what do you use the plus for again?
And uninterpreted functions.
Yeah, QF
it's
Lia
not
plus uninterpreted functions.
It's quantified.
Yeah. So
they are
okay,
quantifiers.
right. Quantified Lia. Okay, so what is the plus for?
What do you mean plus?
Because you have addition, right? So the addition is used for.
Yeah. So you need to add probabilities, right, for reachability.
Okay, but is it integers then in this case? Or?
No, it's not integer.
So it's like real arithmetic?
Real, yeah.
Okay. Do you need any multiplications at all or not really?
Yes, so you need to add and you need to multiply probabilities.
Okay, so then it's like non-linear integer, non-linear arithmetic, right?
And then you have to add the probabilities of different paths, right, for reachability.
Yeah. So that's like non-linear arithmetic then.
Yeah.
Thanks.
Did I say linear?
Yes. It was. Okay. Other questions? So
why do you existentially quantify the factual world? It seems like in a lot of these cases you'd be interested in a particular, you described it as being interested in a particular failure case, but it seems like the problem you're solving is, can I find a factual world such that there is an actual cause? Just wondered why you framed it that way.
Sorry, the framework itself that we're working with works with specific causes. In our case, the specific cause, or sorry, the specific failure we're looking for is the failures in this particular DTMC, in this model.
I see, so the factual is in some sense a run of the model.
Yes.
Okay. Other questions?
Great presentation. I had a question about your results. Could you actually go back? Because
Sure.
I wanted to make sure I saw them right. Otherwise my question will not make sense.
Which page?
Let's see here, this page, and then we go back one other page. Okay, yeah. So I guess my question is so in these two first test cases, we see that both for mountain car and for lunar lander, we get up to seeing about, like, for mountain car, 27,000 states, and for the lunar lander, about 47,000. But the time here, the execution time in that, even for the concrete, is quite short. Whereas if you go to the next slide,
right,
we're seeing like a lower number of states. Like for the F-16 first one, we're seeing about 13,000 and 6,000 for the next one. But the execution time is just much longer. So I was kind of curious, what's the intuition for that? Does this one just have more transitions, or what's the cause of that greatly increased execution time?
So I think it's in two parts. The first one is going to be the F-16 scenario does typically end up with more transitions. However, it also has a lot larger number of state variables.
Mm-hmm. Okay. Cool. Thank you.
I have a question also on this table. So how you choose, in fact, the starting predicates for this abstraction refinement? So this is important in this work because it's not somehow safe.
Right. So the performance really does get impacted by the choice of the initial predicates. For our case, we experimented with finding a reasonable one to use across each case specifically, not line by line, but each case study.
Other questions? So one short question, Steve. Okay. It seems that we are done. Okay, thanks. Thanks.
So the work